minus 3 time, then you can figure out later where exactly that star was overhead at that time. And there's a book for that, which is what we call the Nautical Almanac.
Mhm.
So it basically lists hourly the data of the stars in the sky in general for
What is
every hour.
GMT again?
That's just a Greenwich Mean Time. So it's my time zone. It's the time zone of the clock that I used to get this time, right?
It's not the universal?
The universe will be UTC. So now it's 10 p.m., 10:52 p.m.
GMT. What's the
53 now.
difference between GMT and UTC? I thought that. I mean, I realized they're
Right.
both
UTC is the same thing as
Yeah,
GMT
GMT, right?
plus 0. Let's see.
Yeah.
So UTC is the GMT with no offset. So we don't usually say like UTC plus 3, you say GMT plus 3, but UTC and GMT, they refer to the same time zone, which is like London if they are not in saving times, summertime, whatever you call it. Anyway, so yeah, this is just my time zone. Obviously relevant because this exact time 7:52 is also the same as this, but in the other time zone. So if your clock is using UTC, you're gonna have this as the time. But if it has GMT times 3 minus 3, you're gonna have this at the time. But those are the same time, right?
Mhm.
So obviously the time zone is relevant. But as long as you know the time zone, you can always revert it back to UTC. So the Nautical Almanac lists all the data.
Hello.
Yeah, I see it.
You ever been? Yeah. Have you ever been around? Yeah. You got something? You got something to say?
Do you know? Do you know where the
No,
gold
no.
is? Case,
No, we're on a
case they're
topic,
looking for the
Max.
gold.
Yeah, they're on a topic. You can't just come in and derail the whole thing.
Okay, we're talking about the
Nobody's
important
interested to
issue.
ask you any questions. Nobody wants. Nobody has any questions for you.
It's just a life lesson. If you come into a room, you just gotta wait a couple seconds so you can find out what people are talking about. But anyhow, I was just gonna ask Jay if you
How do you know
ever.
he
You said you know where that is.
So he might have waited patiently, and he didn't know he was in the room, and he would be listening away.
Yeah.
It generally takes more
Well,
than a couple seconds to figure out the topic.
Couple of seconds. That's
Yeah,
hilarious.
Kosha, I know that area.
yeah. I just was wondering if you've ever been over there, walked your dog somewhere in that circle at any point in your life. Uh, if so, yeah, because I might be headed.
Smaller because it would be further. The only place where I could be to have this value is along the circumference of the circle.
Mhm.
And every if we have a bunch of people spread around the circle, every single one of them would measure that same angle to that star. So the HS will be exactly the same for all those people, right?
Right.
So having just the HS doesn't tell me which one of those people I am, because I could be any one of them, which means I can be anywhere along the circle. So how do you solve that? Well, just do it again. Pick another star. So let's say there's a star here. You again measure an angle to that star and your horizon. That's going to give you another value. So you work out again what's the GP of that star. That's going to be a second value of GP and a second distance, because the distance you got now, it's to this star, it comes from a different angle. So that gives you another circle. So if you draw the circle of the places you could be in, it's no longer the same circle as this one. But you have to be
Yeah.
on both at the same time. So the only place where you could be to match both those angles at the same time is at their intersection. So you have an intersection here, and you have an intersection here.
And with
So
this, it's possible to find out 2 possible locations on Earth
Right.
for where I am.
Right, exactly. In that case,
If I get
you
a
have-
third star,
Mhm.
star, then I can narrow it down to 1 possible location on Earth.
That's right. That's right. But this is actually never an issue. You always know which one of those two you are, because you're not drawing a circle on a sphere to figure out where the points intersect. If you did that, you still could figure out which one it is. For example, if you're in this point, then this star is to your left and this star is to your right. If you were in this point, this star will be in your right and this one will be on your left. So the position in the star.
Okay, it's just that I don't know what they're talking. I mean, I understand a little bit, but anyway, let us continue. We were talking about something dark side.
Transposed complex conjugate.
So he's teaching this, but this is not the beginning. Wait a minute, what's going on? How long is this? It says 50, 56, 31. Let's see.
Hello, today we're continuing in our series on quantum mechanics concepts, and we're going to be looking at the position and momentum operators and Heisenberg's uncertainty principle. You may recall from the days of the photon that we could write the state of a photon, let's say that it was at a 45-degree polarized.
Yeah, I've never seen this lecture, so I don't know. Energy operator, I don't know.
Hello, today we're going to continue with our series on quantum mechanics concepts. This time we're going to be looking at the energy operator, which is called the Hamiltonian, and we're also going to be seeing how states vary with time. Hello, today we're going to start a new series on quantum mechanics concepts, and we're going to start with Dirac notation and its simple application to polarization of photons. Before I start, you are about to see some weird notations, and when I first encountered them, I asked myself 2 questions, which you yourself might be asking. The first is, why are we using this most bizarre and peculiar form of notation to represent quantum mechanics? And the only answer I think I can come up with is because it works, because it actually spectacularly represents faithfully what you see in experiment, and I'll show you how. The second question I asked myself was, well, given that's the case, who ever thought that this weird form of mathematical representation might conceivably represent the experimental outcomes of quantum mechanics experiments? And the answer to that, I think you have to say, is, well, that's the definition of a genius. Only someone who was really brilliant, like Paul Dirac, would have been able to see that you could represent quantum mechanics in this way. So I'm going to begin by starting with the notation and a little bit of the mathematics.
I don't think that I don't know if he's a genius. He might be a genius. Probably is, statistically speaking. But from what I heard a lecture about him. So he studied 9 years of technical drawing. Maybe that had to do with it.
Quite a while, we're not going to do any physics at all. We're, as it were, just going to get our chess pieces out so that we understand what the notation is in mathematical terms, and then we will consider how that is reflected in understanding the physics. So notation and maths first. There is a thing called a ket vector. It is denoted in that way. That is called a ket. There is a associated vector, where you'll notice the brackets are the other way round, and that is called a bra vector. I'm afraid Dirac wasn't very creative. The reason he had a bra and a ket is if you put the two together, you get bra-ket. Not very inventive. The ket vector, which we represent, as I said, by A, can also be represented as a column of numbers. A1, A2, A3, all the way down to AN, where N is the number of dimensions you might be considering. All this will become clear when we look at the physics. But in terms of pure notation, in terms of pure mathematics, it's a series of numbers which can be complex numbers. I'll explain what I mean by that in just a moment. On the other hand, a bra vector, which you remember is the other way around, is represented in almost the same way, except that it is a row rather than a column. It still has the numbers A1, A2, A3, all the way up to AN, but those numbers are what's called complex conjugated. And I'll explain exactly what I mean by that. In fact, I better do that now. Firstly, what is a complex number? A complex number, which we sometimes write as Z, is equal to a real number, that can be any number you like, X, plus the imaginary number times a real number, Y. where an imaginary number is the square root of -1. So called because there is no such thing as the square root of -1. There's no solution to the square root of -1. It is imaginary. So a complex number consists of a real number plus another real number but multiplied by the square root of -1. And the two, of course, do not easily combine. Now you can represent a complex number on what's called the complex plane, which is essentially a graph. We would normally call this the x-axis and this the y-axis. But what we now do on a complex plane is we call this the real axis. That's where the real number will be shown. And this is the imaginary axis. So if we have a vector that is x plus iy, that means that we show x, which is the real number on the real plane or the real axis. And we show y, which is the value of the imaginary number on the imaginary axis. And that means that the actual vector itself, z, will equal x plus iy. That's the way we represent it. So z equals x plus iy. And you can see that the modulus of z, that is to say, the actual length of this vector, and I'll say squared, is equal to, by Pythagoras, that is simply going to be this squared plus this squared, which is x squared plus y squared. So the modulus, or in other words, the length of the vector, which is the combination of the real plus the imaginary part, is simply said by, simply given by Pythagoras. Now I mentioned a thing called a complex conjugate, which we denoted by putting an asterisk above the number.
How is this not just vectors, two-dimensional vectors? What's the difference? This is exactly x and y, where x and y are vectors. Whoever invented this didn't want to use vectors, vector notation? I don't get it. This is literally vector notation. So let me Google this or ask ChatGPT. What is the advantage of using complex numbers over vectors? Complex numbers and vectors both represent quantities with magnitude and direction, but they serve different purposes and have distinct advantages depending on the context. Here are some advantages of using complex numbers over vectors. Simpler notation and computation. Okay, let me try something else. Let me ask YouTube. Complex numbers versus vectors. Somebody's asked this before. Let's try this.
Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic, we're going to describe the differences between two-dimensional vectors and complex numbers.
Let me just speed it up.
So, in this topic, we will observe the superficial relationship between 2D vectors and complex numbers. However, we will then delve into looking at the significant differences. We have described two-dimensional vectors, shown here on the left, and complex numbers, shown here on the right in the complex plane. Now, looking at these two vectors, u and v, and complex numbers, w and z, you may notice that there is...
So here's u and v, and here's w and z. So u and v are vectors in vector space, x and y, and w and z are complex numbers in real and imaginary space.
The superficial relationship between these 2 points. Both of these are the same, quote, point, unquote, on the plane. Similar with v and z, these 2 points in the plane seem to occupy the same location.
He said w, oh, v and z, and u and w. Okay, so u and w is the same location, and v and z are the same location.
So the question is, why do we use one versus the other? Now, for a vector, each entry represents a separate piece of independent information. A complex number, on the other hand, is a single value. It is no different than a real number, and if you start taking either the real or imaginary components, you no longer have the original number. For a vector, we're not going to have a useful definition of multiplication that works not only in R2, but also in R to the n. On the other hand, multiplication...
What?
Of complex numbers is well defined and has a significance that is applicable in a number of different areas. Now,
so it's just different tools for different jobs, just different definitions, I guess.
For a vector, there is no real significance to the vector 1, 0. Yes, it's a unit vector, but beyond that, it's not significantly different from 0, 1. For complex numbers, however, the analogous value, which is just 1 plus 0j, that is the value such that 1 times z is equal to z for all z, and every non-zero complex number, z, has a reciprocal such that z times z inverse is equal to 1.
I didn't get that.
Now, recall that the vector u, 7.6, negative 8.2, does represent a point in the plane, yet there's no real reason or real significance between this point and the point v, which is equal to 0.0608 and 0.0656. However, you may note that the product of the 2 corresponding complex numbers is indeed equal to exactly 1. The question is, what are we modeling? There are only very limited numbers of applications of complex numbers, but for those applications, complex numbers are ideal. For example, in finding solutions to differential equations, simulating sinusoidal functions with equal period, specifically alternating current. However, this can also simulate, for example, motions in an engine. Finally, quantum mechanics, and this is what you will see in your second-year course. On the other hand, two-dimensionals are much more ubiquitous. Basically, a two-dimensional vector is just ordered information. Now, just as a historical comment, as you may be interested, vectors only came to prominence in the 1800s, late 1800s actually. Prior to that, William Hamilton actually introduced something called quaternions, and quaternions had 4 components, so they were a generalization of complex numbers. However, they had a problem. For a multiplication to be defined on...
Did he say they were a generalization of complex numbers?
Generalization of complex numbers. Do something called quaternions, and quaternions had 4 components, so they were a generalization of complex numbers.
Quaternions were a generalization of complex numbers? Am I hearing right?
Quaternions, and quaternions had 4 components, so they were a generalization of complex numbers. However, they had a problem. For a multiplication to be defined on quaternions, it ends up that the resulting multiplication is not even commutative. So multiplying a quaternion q times a quaternion p may not give you the same value as multiplying p by u. Now, quaternions do still have applications today in graphics, but that seems to be about the one limited application thereof. There's actually an 8-dimensional number system called the octonions, but for that, the multiplication you end up is not even associative. So you actually have to worry about, are you multiplying a by b first and then multiplying by c, or are you multiplying b by c first and then multiplying the result by a? So not very useful or applicable. Another point is you simply cannot create a multiplication that is reasonably well-defined, for example, where there's existence of reciprocals for anything other than powers of 2. So there really is nothing analogous to R3 with respect to numbering systems such as the quaternions or complex numbers. So yes, vectors are much more general, as vectors are well-defined for all dimensions from 1 up to however large you require. So following this topic, you now understand two-dimensional vectors and complex numbers do indeed represent separate ideas. You know that the first has 2 components while the second is a single value, and you understand that for vectors there is no significance to the reciprocal of their corresponding complex values. Here's the references, acknowledgements, colophon, and a disclaimer. Cheers.
I'm not sure I understand.
Quantum mechanics is a notoriously complicated and confusing subject. And part of that is for good reason. I mean, there really are these crazy phenomena happening in the quantum world that are challenging to imagine. But one of the reasons quantum mechanics is complicated is that there are all these complex numbers all over the place. And at first, when you're getting into the subject, it's very confusing. Why are we using complex numbers? What do they mean? Why can't we use real numbers? Isn't this physics, not math? Why do we use these crazy numbers, right? So that was the source of confusion for me, at least, for quite a long period.
This guy sounds gay. He's always laughing. So he's funny, but I think he's gay.
Time. And then one day it clicked, and I finally understood, and I was like, oh, okay, yeah, actually, that complex numbers are what we want to use in quantum mechanics. So what are the complex numbers anyway? I think the most defining feature of the complex numbers is that they're a 2-dimensional number, and that seems scandalous. But if you've been using the real number line, then you're already kind of complicit in using a 2-dimensional number system, sort of. Because when you write a real number, you write its magnitude, but you also assign it to one of the 2 number rays, either positive or negative. So you already have this sense of magnitude and direction in your number system. It's just that you only have 2 options for the direction, positive or negative. So the direction dimension of the real numbers is just a discrete binary thing rather than a continuous thing. And all the complex numbers really are is a generalization of that positive-negative binary. That is, the complex numbers can be regarded as a generalization of positivity and negativity. So that a number can be not only on either the positive or negative number ray, but also all of the number rays in between. This is a very strange concept the first time you see it. Now, if you're mostly used to using numbers to count things, this seems like an affront to reason. Because after all, if you consider the number 2, for example, so you could have positive 2, you could have negative 2. But with the complex numbers, you can also have this 2 that's just somewhere in this space of, somewhere in the circle that has radius 2. The number with magnitude 2 in the complex plane can be at any one of these points. And that doesn't seem right, because you'll notice when 2 is up, just purely pointing straight up, then it's neither positive nor negative. And yet it's still 2. It still has the amplitude of 2. That doesn't really fit into our normal intuitions about counting, right? It doesn't feel like it makes sense. Okay, but complex numbers are not about counting in this kind of way. Let's look at this. This is a wave. What kind of wave? I don't know. Could be the surface of the ocean. It could be a sound wave where the height represents the air pressure. It could be a wave of light just flopping around in the electromagnetic field. Whatever it is, it's just a wave. Now, this is a very clean and pure wave that I'm using to illustrate the point, but it's a wave nonetheless. So how can we use numbers to capture what this wave is? Well, the first and most obvious thing is if the wave is above the average level, if the wave is up, we'll say it's a positive number. And if the wave is down, we'll say it's a negative number. So let's go ahead and color it in positive and negative. All right, fair enough. It's not wrong. But let's pause time for a second. Now look here. Right at the point where the wave is 0 and going down, is that point really 0, or does that point exist in a harmonious continuum with the rest of the wave? Yeah, it's 0 now, but it's part of a bigger picture, and you know it's just going to be changing soon. You know it'll soon be non-zero, so is that really 0 in the same way that a flat line is 0? Or does it somehow have an amplitude, even though it's also kind of 0 at the same time? So do you see an analogy between this thing that's kind of 0 and kind of not 0, and the example we were looking at earlier when the 2 was pointing straight up, and it was also kind of 0 and kind of not 0? Now what's more, look at this point over here, where it's also 0, but now it's going up. All of the same observations apply. It's kind of 0, but it's not really, it has some energy to it. Even though it's 0, it's kind of is, kind of isn't. So now we can see that this number here is the opposite of the previous number that we were looking at, because the previous one is on its way down, and this one is on its way up. Let's transform our perspective and use complex numbers to represent this wave. This is what a complex wave looks like. Notice that the amplitude is constant, and it's just the phase that's changing. So it's not moving up and down like the other wave. Now, this is a very pure wave. This is a wave of the form e to the I theta, where in this case, theta is some function of x and some function of time. Now let's plot the real part of this complex number, that is, how far left or right the number is in the complex plane, and you'll see that we can recover that wave we were looking at earlier. Let's show the imaginary component of this complex wave, that is, how far up and down the wave is in the complex plane, and you'll notice here we get a wave that looks very similar to the real part, but it's out of phase, such that it takes on maximum and minimum values when the real part is at 0, and vice versa. By the way, the function e to the I theta is equal to cosine of theta plus I times the sine of theta, where I is the imaginary unit. This equation is known as Euler's formula, well, one of his many formulas, and it gives us another way of thinking about what this complex wave is. When you're first getting into complex numbers, you will probably think about Euler's formula as the definition of what e to the I theta is, but as you become more comfortable with e to the I theta, you'll eventually just see that as the wave, and then the cosine and sine is a way of splitting it up into the real part and the imaginary part. By the way, let me just quickly say, on the topic of the imaginary part, imaginary numbers are a misnomer, okay? They're just as real or just as imaginary as the real numbers. The complex numbers are a numerical structure, they're a holistic thing. You know, it doesn't make any sense to say imaginary and real, but whatever, this is the terminology you're stuck with, so it is what it is. Ultimately, it's the consequence of the fact that the imaginary numbers were names before they were understood, and that's, I think, one of Descartes' greatest mistakes. Well, that and dualism, but anyway, where were we? What are we talking about here? To understand why it's useful to be able to represent a wave as a constant amplitude complex number whose phase is changing, we'll have to take a look at the nature of complex addition, multiplication, and how this relates to wave interference. We'll do that in a moment, but first I want to make a quick comment about why is it e to the I theta gives us this wave. I don't have time in this video to give a really satisfactory answer, but I can lead you in the right direction. So if you take derivatives of e to the I theta and sine of theta and cosine of theta, you can write these functions in terms of a Taylor series. When you do that, you'll find that e to the I theta has a term of theta at every degree, whereas cosine has even terms and sine has odd.
Wait, did he say if you take a derivative of both sides, that's what you get?
Answer, but I can lead you in the right direction. So if you take derivatives of e to the I theta and sine of theta and cosine of theta, you can write these functions in terms of a Taylor series.
No, it's either if you take a derivative or if you do a Taylor expansion. You don't do both. Why would you want to do both? This what you did here is a Taylor expansion, isn't it? I don't know.
When you do that, you'll find that e to the I theta has a term of theta at every degree, whereas cosine has even terms and sine has odd terms. And if you look closely at these series, you can see that the terms on the right-hand side of the equation zip together into the terms on the left-hand side of the equation. So by taking Taylor series, you can prove to yourself that in fact e to the I theta is cosine of theta plus I sine of theta. Okay, so that was a bit of a tangent, but I think it's important for you to know. Now let's take a look at complex addition. If we have any two complex numbers, we can add them just like they're vectors. So we put them tail to tip, or another way of looking at it is the sum is the diagonal of a parallelogram.
Okay, I have no idea what he's talking about. I got absolutely nothing from this video.
So, in this topic, we will observe the
So we're going to talk first about how we use complex numbers in both the Cartesian form and the polar form, and in particular, I'll emphasize.
I saw this lecture.
So we're going to talk first about how we use complex numbers in both the Cartesian form and the polar form, and in particular, I'll emphasize.
Complex numbers as vectors. So a vector is fully defined by magnitude and direction. And we've kind of seen a little bit of this before with complex numbers. So if we draw up our Argand diagram, we get our real axis and our imaginary axis. And we know a complex number can be represented by either in Cartesian form or mod arg form. And we're going to be interested in here for mod arg form. So if we have some complex number z, we can say that its distance away from the origin is its modulus, and the angle theta it makes with the positive real axis is its argument. So this theta is just the argument of z. And this fully defines the complex number, and we can treat it as a vector going from the origin to that point. And some things about vectors we can look at. If we have our real axis and imaginary axis, if we have some complex number, z1 that was out here, and another one, z2 that was out here, and we treated them as vectors, we could say that the addition of those vectors form a parallelogram. So we could imagine an identical z2 here, and an identical z1 here, and the parallelogram that it forms is the equivalent vector of this diagonal to be z1 plus z2. Now, the diagonal going from z2 to z1 gives us the vector z2 minus z1, and the vector going from z1 to z2 gives us z1 minus z2. Also, we know this angle here is the argument of z1. This angle here is the argument of z1 plus z2. And also, if we extend z2 minus z1 over here, we get this angle being the argument of z2 minus z1. Let's have another look at an interesting property with vectors. Let's draw up another Argand diagram with real and imaginary axis. And let's draw in a simple vector that goes from the origin to the point 1. And let's call this complex number z. And z will just has a real part of 1 and no imaginary part. So essentially, this complex number is just equal to 1. Let's multiply this complex number by I. So multiplying both sides by I, we get zi. Now 1 times I is just I. And let's go ahead and draw our new complex number. So now we have the complex number 0 plus 1i.
So z equals 1. So zi is equal just I. Which is, it's equal to I, or 0 plus 1i.
And that complex number, or vector, is this, going through the point 1 on the imaginary axis. Let's again multiply both sides by I. So then we get z times I squared. And 0 times I is 0, and I times I is I squared, which we know is equal to minus 1. And this can be represented as minus 1 plus 0i. And let's go ahead and draw this vector in here. So we get minus 1 plus 0i, which is purely on the real axis, going to minus 1. Let's again multiply both sides by I. So we're up to zi cubed. I know we can simplify these, but we'll leave them as this. Minus 1 times I is minus I, and 0i times I is just 0. And let's go ahead and plot this, and that's just equivalent to 0 minus 1i. And if we plot this, we're down here, going to minus 1 on the imaginary axis. And finally, let's again multiply both sides by I. So we get zi to the 4, and 0 times I is 0, and minus 1i times I gives us minus I squared, and I squared is minus 1, minus times minus 1 gives us 1, and that's equivalent to 1 plus 0i. And if we plot that, we're back over here, going to 1. So why did we go through all of that? So the reason we went through all of that is we have an interesting property if we're looking at complex numbers as vectors. When we multiply a vector by I, it rotates the vector counterclockwise. Rotates the vector counterclockwise by pi on 2 radians every time we multiply by I. Let's have a look at an example. We're going to let z and w be two complex numbers. We're going to say if the modulus of z equals the modulus of w, we want to show that z plus w divided by z minus w is purely imaginary. And another way to say that is that if this was equal to some other complex number p,
the real equals 0. Real of p equals 0.
We can say that the real part of p has to equal 0.
So what's the definition of the modulus of z?
So let's draw a diagram to help us out. So we're drawing an Argand diagram.
Is the modulus the square root of the square of the real plus the square of the imaginary?
Real axis and imaginary axis. Let's draw in any complex number z. Let's say here, say z is there, and w, but we do know that their modulus have to be equal, so we'll try and make them the same distance apart, or the same length. So say another one w, we're trying to make those lengths the same. And we have expressions for z plus w and z minus.
So we already said z plus w and z minus w. We know what those look like. So z plus w, we said we draw a parallelogram, and that this point is z plus, and z minus w, I think, is this vector. So the length of this vector is the same as this vector? The length? No, that's not what we're saying. We're saying that the real, this vector, the real is 0. If the real is 0, it must be over here. I don't know.
Minus w. And usually when you have these kind of expressions, it hints at the fact of drawing a parallelogram. Let's go ahead and draw some expressions in. So z plus w, again, we can imagine shifting these vectors like so, and connecting this part to get our expression for z plus w. And our expression
z minus w is the line from the vector from z to w.
and for z minus w will be going from w to z.
Oh, w to z, okay.
So this is our z minus w. Now, if the modulus of z equals the modulus of w, this means that we now have a rhombus here. And if we have a rhombus, the intersection of the diagonals has to be at 90 degrees, which means that if we take this vector, z minus w, and multiply it by I, we rotate it pi on 2 radians.
Then it should be exactly z plus w. So you're saying that z minus w times I should be identical to z plus w.
Counterclockwise, and it ends up being in the same direction as z plus w. So that's right.
Oh, just the same direction? Oh, yeah. We don't need the length. Oh, the length is equal. Z and w are equal length. It's given that z, the absolute value of z, the modulus of z is equal to the modulus of w. What's the I don't remember the definition of the modulus. It was like the first thing that he discussed.
With the positive real axis, we can say that it's mod arg form. And we're going to be interested in here for mod arg form. So if we have some complex number z, we can say that its distance away from the origin is its modulus. And the angle theta it makes with the positive
Oh, he didn't define modulus.
real axis going from the z1, z2, z1. We know this. All this complex.
I don't know what
vector
modulus is. It
is
doesn't
this.
matter. Okay, it doesn't matter.
Hi, everyone. My name is Dego, and I want to just share something I learned that is pretty interesting.
Let's say we're given the function f of x is equal to x squared plus 1. We can graph our function and get a nice parabola. Now, let's say we want to figure out where the equation equals 0. We want to find the roots. On our plot, this should be where the function crosses the x-axis. As we can see, our parabola actually never crosses the x-axis. So according to our plot, there are no solutions to the equation x squared plus 1 is equal to 0. But there's a small problem. A little over 200 years ago, a smart guy named Gauss proved that every polynomial equation of degree n has exactly n roots. Our polynomial has a highest power, or degree, of 2, so we should have 2 roots. And Gauss's discovery is not just some random rule. Today we call it the fundamental theorem of algebra. So our plot seems to disagree with something so important, it's called the fundamental theorem of algebra, which might be a problem. What Gauss is telling us here is that there are 2 perfectly good values of x that we could plug into our function and get 0 out. Where could these 2 missing roots be? The short answer here is that we don't have enough numbers. We typically think of numbers existing on a one-dimensional continuum, the number line. All our friends are here: 0, 1, negative numbers, fractions, and even irrational numbers like root 2 show up. But this system is incomplete. And our missing numbers are not just further left or right, they live in a whole new dimension. Algebraically, this new dimension has everything to do with a problem that was considered impossible for over 2,000 years, the square root of -1. When we include this missing dimension in our analysis, our parabola gets way more interesting. Now that our input numbers are in their full 2-dimensional form, we can see how our function x squared plus 1 really behaves. Our function does cross the x-axis. We were just looking in the wrong dimension. So why is this extra dimension that numbers possess not common knowledge? Part of the reason is that it has been given a terrible, terrible name. A name that suggests that these numbers aren't even real. In fact, Gauss himself had something to say about this naming convention.
I hate it when they expect me to read something so long. But what did he say? That this subject imaginary numbers has hitherto been surrounded by mysterious obscurity is to be attributed largely to an ill-adapted notation. If, for example, +1, -1, and the square root of -1 had been called direct, inverse, and lateral units instead of positive, negative, and imaginary, or even impossible, such an obscurity would have been out of the question.
So yes, our missing dimension is comprised of numbers that have been given the ridiculous name imaginary. Gauss proposed these numbers should instead be given the name lateral. So from here on, let's let lateral mean imaginary. To get a better handle on imaginary, I mean lateral numbers, and really understand what's going on here, let's spend a little more time thinking about numbers themselves. Early humans really only had use for the natural numbers, that is 1, 2, 3, and so on. This makes sense because of how numbers were used. So to early
Those are natural. Okay, bro, how many water buffalo are over there? 6, dude.
humans, the number line would have just been a series of dots. As civilizations advanced, people
Yep, those are definitely all the numbers. Any more would be ridiculous.
needed answers to more sophisticated math questions, like when to plant seeds, how to divide land,
Bro, when should I plant these seeds?
and how to keep track of financial transactions. The natural numbers just weren't cutting anymore, so the Egyptians innovated and developed a new high-tech solution: fractions. Fractions filled the gaps in our number line and were basically cutting-edge technology for a couple thousand years. The next big innovations to hit the number line were the numbers 0 and negative numbers, but it took some time to get everyone on board. Since it's not obvious what these numbers mean or how they fit into the real world, 0 and negative numbers were met with skepticism and largely avoided or ignored. Some cultures were more suspicious than others, depending largely on how people viewed the connection between mathematics and reality. And this is not all ancient history. Just a few centuries ago, mathematicians would intentionally move terms around to avoid having negatives show up in their equations. Suspicion of 0 and negative numbers did eventually fade, partially because negatives are useful for expressing concepts like debt, but mostly just because negatives kept sneaking into mathematics. It turns out there's a whole lot of math you just can't do if you don't allow negative numbers to play. Without negatives, simple algebra problems like x plus 3 equals 2 have no answer. Before negatives were accepted, this problem would have had no solution, just like we thought our original problem had no solution. The thing is, it's not crazy or weird to think these problems have no solutions. In words, this algebra problem basically says, if I have 2 things and I take away 3, how many things do I have left? It's not surprising that most people who have lived on our planet would be suspicious of questions like this. These problems don't make much sense. Even the brilliant mathematicians of the 18th century, such as Euler, didn't really know what to do with negatives. He at one point wrote that negatives were greater than infinity. So it's fair to say that negative and imaginary numbers raise lots of very good, very valid questions. Like, why do we require students to understand and work with numbers that eluded the greatest mathematical minds for thousands of years? Why did we even come to accept negative and imaginary numbers in the first place when they don't really seem to be connected to anything in the real world? And how do these extra numbers help us explain the missing solutions to our problem? Next time, we'll begin to address these questions by going way back to the discovery of imaginary numbers.
Wow, really interesting.
Plot.
Earlier on in a calculus or linear algebra course, you may have seen that points in the plane and vectors from the origin to a point in the plane are identified used interchangeably. We can do this with complex plane too. We can view complex numbers z equals x plus iy as a vector from the origin to the point x, y. This is useful if we want to apply geometric properties, which we know from vectors to complex numbers, as you will see in this video. So what I'm going to do, I'm going to take a point z equals x plus iy, and the vector is components x and y, and we both plot them in the complex plane. Here is complex number z and the vector from the origin to z. And then we see that certain properties are the same for vectors and for complex numbers. For example, if we add to...
Wow, he's reuse allowed. .465 views, no comments. Yeah, he's very difficult to understand.
Two vectors, v1 and v2. You add x.
Plus the audio is really terrible.
Why do trig functions appear in Euler's formula? This was the question I had when I...
A huge thanks to Squarespace for sponsoring this video. Hey everyone, Parth here, and in this video I want to talk about complex numbers and how they can be used in physics. We'll start by looking at the absolute basics of complex and imaginary numbers and then apply these to a few areas of physics. So if you enjoyed this video, then please hit the thumbs up button and subscribe for more fun physics content. Let's get into it. Now, if at any point we cover something that you're already familiar with, then check out the timestamps at the bottom of the video player and feel free to skip ahead. Okay, let's start by looking at what an imaginary number is. The imaginary number I is defined as being the square root of -1. In school, we're often taught that only positive numbers can have a square root, but at some point someone thought, what if we could find the square root of negative numbers? The imaginary number I was defined as the square root of -1, and it's only called imaginary because back then it was considered fake or useless, but it's just a name. Anyway, using the simple imaginary number that we defined, we can write the square root of any negative number. For example, we can find the square root of -4 because -4 is equal to -1 times 4. Then using the rules of surds or square roots, we can say that the square root of -4 is 2 times I, the imaginary number. Or the square root of -7 can be written as I
Okay.
times the square root of +7, which is approximately this number here. So that's an imaginary number, something multiplied by this quantity that we're calling I. It doesn't actually fall on the number line that we're used to, but we'll come to that in a moment. In order to get there, we first need to look at how imaginary numbers can be combined with non-imaginary or real numbers. We do this by simply adding together a real number and an imaginary number. For example, 5 plus 2i. This whole thing, a real number added to an imaginary number, is called a complex number. Again, that's just what it's called. Doesn't really matter what we call it, as long as we all know what's being discussed. We could call this combination Jeff if we wanted to, but we won't. So let's take a look at how we can combine two Jeff numbers, complex numbers. Let's say we want to find this complex number plus this complex number. Well, we simply sum together the real parts and the imaginary parts separately to give us our final result. Easy. And here's how we can multiply complex numbers together. This will be intuitive if we know how to multiply out brackets with multiple terms, but notice that this first term here gives us a real number. The second and third terms are imaginary because we multiplied an imaginary number by a real one, and this final term has this I squared bit in it. But what is I squared? Well, it's just -1. So this final term is also real. We can then simplify this by collecting reals and imaginaries together to give us our final answer. So this is how complex numbers work. We can treat each component separately. And there's a reason that I'm saying component. To see what I'm talking about, let's take a look at a way to represent complex numbers in a graphic or diagrammatic way. Firstly, we draw a number line with all our real numbers on it. 0 in the middle, negative numbers to the left, and positive numbers to the right. Now, we said earlier that I, the root of -1, is not a real number, so it doesn't lie along this number line. We can choose to represent the imaginary number on another axis. We can imagine I lies along this line here. And this value is twice the distance from the origin of our newly forming graph, so this is 2i, and then we've got 3i, and so on and so forth. And of course, we have negative imaginary numbers too. What we've drawn here is known as an Argand diagram, and we can represent any complex number on it. For example, our complex number 4 plus 3i can easily be represented by starting at 0, going 4 units along the positive real direction, and then 3 units in the positive imaginary direction. And this point on our diagram then represents the complex number 4 plus 3i. Now, interestingly, we can also represent the same number with a vector or arrow starting at the origin and ending at our point here. This way, each of the parts of our number, the real part and the imaginary part, act like the horizontal and vertical components of the vector. And this is why we can treat each part separately, because we treat them as if they're acting in perpendicular directions, the real direction and the imaginary direction in this abstract space of numbers that we've just created. Now, each complex number obviously has its real and imaginary parts, but it can be also described using two different pieces of information. Firstly, we can use the length of the vector drawn here. We can call this the modulus or absolute value of the complex number, and it's easily found using Pythagoras' theorem. The other important defining quantity is an angle.
Okay, so that's the modulus is Pythagorean length.
We normally use the angle between the real axis and the complex number vector measured in the anti-clockwise direction. This is just a choice, but usually a very convenient one. This angle, usually labeled theta, is called the argument of the complex number. And just like we can figure out uniquely which complex number someone is talking about if we know its real and imaginary parts, we can do the same if we just know the absolute value and the argument, because the absolute value tells us how long our vector is starting at the origin, and our
He didn't say what an argument is.
argument tells us what angle it has with the real axis. Okay, now this next bit is where we start seeing links
So the argument is just the angle.
with small bits of physics, though it might just complex numbers of information. Firstly, we can use the length of the vector drawn here. We can call this the modulus or absolute value of the complex number, and it's easily found using Pythagoras' theorem. The other important defining quantity is an angle. We normally use the angle between the real axis and the complex number vector measured in the anti-clockwise direction. This is just a choice, but usually a very convenient one. This angle, usually labeled theta, is called the argument of the complex number.
It's called the argument of the what?
Clockwise direction. This is just a choice, but usually a very convenient one. This angle, usually labeled theta, is called the argument of the complex number. And just like we can figure out uniquely which complex number someone is talking about if we know its real and imaginary parts, we can do the same if we just know the absolute value and the argument, because the absolute value tells us how long our vector is starting at the origin, and our argument tells us what angle it has with the real axis. Which complex number someone is talking about if we know its real and imaginary parts, we can do the same if we just know the absolute value and the argument, because the absolute value tells us how long our
So you can specify the absolute value on the argument, which is the length and the angle.
Our vector is starting at the origin, and our argument tells us what angle it has with the real axis. Argument, because the absolute value tells us how long our vector is starting at the origin, and our argument tells us what angle it has with the real axis. Okay, now this next bit is where we start seeing links with small bits of physics, though it might not seem obvious at first. Let's remember, using trigonometric identities, that the cosine of an angle in a right angle triangle, like this one, is given by the size of the adjacent side divided by the size or length of the hypotenuse. And so the hypotenuse, which is r, multiplied by the cosine of the argument theta, gives us the real part of the complex number. Then we can do
The cosine of theta is the real of the complex over the length.
Similar thing with sine. The sine of theta is given by the length of the opposite side to the angle
The sine is the imaginary over the length.
divided by the hypotenuse. So we can say r sine theta is equal to the imaginary part. In other words, we can now say our complex number is given by r times cos theta plus I times r times sine theta. Factorizing the r, we find that this is r cos theta plus I sine theta. This is often really
So z is the real of z plus I, the imaginary of z, or it's the length times the cosine theta plus I times r times the sine of theta. R sine theta is the imaginary, r cos theta is the real, or you can pull out the r and z is equal to r cos theta plus I sine theta. The length. Okay, it's just algebra.
useful in physics because we describe many things using sine and cosine functions like transverse waves such as light or the oscillation of a pendulum or many other such things that you can think of. But here's the thing, this whole bit inside brackets can be written much more compactly using exponential functions. We may be most familiar with the exponential function as representing things that grow more and more quickly over time. But what we specifically call the exponential function is a very interesting one. In its most basic form, its value at every point is equal to the gradient or slope of the function at that same point. Anyway, when combined with complex numbers, it can also be used to very concisely represent sine and cosine functions. More precisely, it turns out that our complex number, r times cos theta plus I sine theta, can be represented as r times e to the power of I times theta. This identity here is known as Euler's identity, and it would take a whole video to discuss properly. I'll also leave some resources in the description below if you want to find out why this identity is true, since it might seem very confusing that an exponential function suddenly looks periodic when we introduce complex numbers into it. The reality is a little bit more subtle, but like I say, resources in the description below.
You could have taken less time by saying, if you want to prove, just take the derivative of the equation and you'll see that it's the same.
And let me know if you want me to make a separate video on this. But here, let's just assume that this identity works. There are a couple of benefits to this. Firstly, it's the compact packaging. Quite literally, it's shorter and easier to write e to the power of I theta rather than the whole cos theta plus I sine theta every single time. But secondly,
Okay, yeah, that's true.
when dealing with multiple complex numbers, it's easier to deal with the exponential notation than it is to deal with sines and cosines. For example, when multiplying two complex numbers using the sine and cosine notation, we'd have to do this whole thing, as we've already seen earlier in the video. Whereas with the exponential notation, using the roles of exponentials, we simply add the exponents and get
Interesting. But why do you need the I? What's the benefit of modeling a physical phenomenon with the I?
our end result. Much simpler. What we'll look at next takes us closer still to how complex exponentials are used in physics. We often have to represent physical systems with just sines or just cosines. For example, we can describe the oscillation of a mass on a spring over time using a cosine function. What this tells us is that as time passes, the position of the block changes following a cosine form. Now, we know that sines and cosines are included within this complex number form, but actually we just want to work with one of these, usually the real part. However, it's often easier just to work with this whole extended complex exponential form, do whatever mathematics we need to do to study the system, and then at the end, take the real part of the result. Which essentially just means to read out the real part and ignore everything imaginary. Like I say, this is often easier than just dealing with the cosine function individually and potentially having to multiply and add other functions to this. Another area of physics where this exact same idea can be used is
That's interesting. So the reason is convenience.
in the study of alternating currents in electric circuits. Often, an alternating power source will output a sinusoidal potential difference or voltage, and this will influence the current or flow of charged particles that get set up in the circuit. If we just have resistors of different kinds in the circuit, then to be honest, it's easier to deal with the sines and cosines.
I'm still blown away how they couldn't believe that the ether gives you special relativity. I mean, special relativity comes out of the ether. They couldn't believe it. They wanted to kill themselves when they heard it today. That was so funny.
Usually, because the current in the circuit will have a peak value given by Ohm's law, not technically Ohm's law. Check out this video up here if you want to know more, but the voltage and current will be in phase. That's what's important here. What this means is that the peaks and troughs in the current in the circuit occur at the same time as the peaks and troughs in the potential difference or voltage supplied by the power source. However, if we have other components like capacitors and inductors in the circuit, we have to suddenly deal with the fact that the current may not peak at the same time as the voltage. We say that the current and voltage in these particular instances are not in phase, or they have a phase difference. This is because of the specific behaviors of capacitors and inductors. By the way, I want to make a video discussing electric circuits in 5 levels of difficulty, all the way from beginner to advanced, so let me know if you'd be interested in seeing that in the comments down below. The point is, though, that once we start dealing with phase differences and actually calculating these phase differences, it often becomes easier to deal with complex exponentials simply because these are mathematically more compact and easier to deal with, and then just take the real part like we discussed earlier. So technically the complex part or complex numbers aren't necessary to represent the system mathematically, but their use makes life a lot easier. However, there is one area of physics where complex numbers are absolutely essential in representing the full picture rather than just acting as a
Schrodinger's equation.
mathematical convenience. We are of course talking about quantum physics. In quantum physics, every single system that we study, maybe a single electron, or maybe the proton and electron in a hydrogen atom, or anything else that we could study, can be represented by a wave function. This wave function contains all the information we can know about our system, such as the positions in space in which we're most likely to find our particles if we measure them. And the wave function is inherently a complex function. The complexness of it is very important. Now, there's a slight subtlety about this that I want to quickly mention here. When we make any measurement on the quantum system that we're studying, like for example, looking for the positions of our system's particles, what we directly measure is something to do with the wave function squared, technically the square modulus. This is because the square modulus of the wave function is directly related to the probability of getting a certain measurement result, such as finding one of our particles at this point in space, for example. And when we find the square modulus of the wave function, the complexness actually goes away. We're left with a real number, which makes sense because probability needs to be a real number. You can't have a 3i% chance of finding a particle somewhere in space. So in that sense, the complexness of the wave function is lost, and we may think that the complexness is once again a mathematical convenience in order to represent quantum wave functions, and that it isn't actually significant in terms of the physics. However, this is not true. There are quantum effects that are directly or indirectly impacted by the complex phase of wave functions, which have calculable and measurable indirect effects. One such effect is the Aharonov-Bohm effect, which I discussed in this video up here if you're interested. But to me, it's very cool how complex numbers have an indirect but measurable impact on quantum mechanical systems. Now, before we finish up, I want to take a moment to thank the sponsor of this video, Squarespace. Squarespace is...
Okay, so he didn't say it's Heisenberg.
Why the trick?
A huge...
Professor Dave here. Let's look at complex matrices.
He knows a lot about all kinds of stuff.
Professor Dave here. Let's look at complex matrices.
He knows a lot about
matrices where all of the entries are real numbers. Now it's time to consider complex matrices, which are matrices in which some of the entries contain complex numbers. If you need a little review regarding complex numbers, what they are, and relevant operations, check out this tutorial from earlier in the series. Otherwise, let's dive right in. We can simply recall that complex numbers are numbers with a real part a and an imaginary part bi, where I is the square root of -1. And as we said, we can find complex numbers in matrices. Just the way we can separate complex numbers into a real component and an imaginary component, we can separate matrices into a real matrix A and an imaginary matrix IB. For example, let's consider the 2 by 3 matrix, 2 plus 3i, I, 6 minus 4i, 7, 2 minus 3i, negative I. We can split this complex matrix up into a real part plus an imaginary part by keeping in mind that matrix addition works element by element. First, for the real part, we just take the real part of each element and put them in a matrix of the same size. So for the first entry, we take the 2 from 2 plus 3i. Continuing in this manner will give us 2, 0, 6, 7, 2, 0. Then we do this again for the imaginary part of each element. So this time we take the 3i from 2 plus 3i. That will give us I times 3, 1, -4, 0, -3, -1. We could distribute the I and add the two matrices together to get what we started with. Now that we know what complex matrices are, we must consider the complex conjugates of matrices. Recall that for ordinary complex numbers, we learned that the complex conjugate is the same as switching the sign on the imaginary term. So a plus bi would become a minus bi. Similarly, the conjugate of a complex matrix, a plus ib, is simply a minus ib. We actually don't even have to take the step of splitting up the real and complex parts. The conjugate of a matrix can be found immediately by switching the sign on every I term in the matrix. So with our previous example, 2 plus 3i, I, 6 minus 4i, 7, 2 minus 3i, negative I, the conjugate will be 2 minus 3i, negative I, 6 plus 4i, 7, 2 plus 3i, I. So this is certainly simple enough. However, when it comes to matrices, there is another operation that is much more important than taking the conjugate, and this is taking the conjugate transpose. Finding this is not too difficult. You simply take the conjugate, as we just did, and then take the transpose of the matrix, which, as we recall, involves making the columns into rows and the rows into columns. The reason we want to do this is so that we can multiply the matrix and the conjugate transpose. Simply taking the conjugate will not give us matrices we can multiply if they are not square. For example, our 2 by 3 matrix cannot be multiplied by its 2 by 3 conjugate because of the way matrix multiplication works, which we recall from a previous tutorial. But if we take the transpose of the conjugate, we will get a 3 by 2 matrix, and now we can multiply them with no problem. We've already seen that the conjugate was 2 minus 3i, negative I, 6 plus 4i, 7, 2 plus 3i, I. So taking the transpose, we will get 2 minus 3i, 7, negative I, 2 plus 3i, 6 plus 4i, I. This is our conjugate transpose, also referred to as the Hermitian transpose. Given a matrix M, the notation for taking the...
That's called the Hermitian? Really?
Conjugate transpose is MH, or in some fields, an M with this symbol, read as M dagger.
Wow. Fascinating. Why is there 2 people watching?
Professor Dave here. Let's
Okay, let's get back. Let me just close some windows. Let me close some windows. Okay, I think we're back to here. This is today's video. Let's just make sure that
See
it's
again?
that it's
as long as you know the
fine.
time.
1, 2, 3, 4. Let me close some windows. It's fine. It's fine. Let's see if there's anything interesting. Patrick Bet David unable to accept that Trump is losing bad on Fox. Cope. Oh, okay. The Sam Cedar caller says Sam is doing the show wrong. Prep for scientific paper submittal.
Good day to you. This is Anna Galactic bringing you another presentation in cosmic geometry.
Forget it.
Good day to you. This is Anna Galactic bringing you another presentation in cosmic geometry.
Celebrating life, every dog comes his day. Hassan Nasrallah, beautiful dog death. Beautiful dog. He was a beautiful dog. I love dogs.
Tiny gravitational redshift that should occur everywhere and every when in the universe. Once at initial position and velocity, bodies in a gravitational field seem
All right, I think we can continue.
That means the complex conjugate of z. And what is this weird thing? Well, it couldn't be simpler. It's simply the same value of x, but you change the sign of the imaginary term. So if z is x plus iy, the complex conjugate is x minus iy. And you can, I think, fairly easily see that the complex conjugate of the complex conjugate, if you do it twice, that will be you change the sign again, and you get back to where you started. So the complex conjugate of a complex conjugate is the number you started with. And I can represent this complex conjugate also on the complex plane. X remains the same, so the x dimension will be the same, but the imaginary term has changed signs. So now we're going to be at minus y, and consequently the vector.
Hold on, I'm gonna go get some gum. I'll be right back. You know what? I'll let it play, and we'll come back. I'll play it again. So we're at 6:46.
Z complex conjugate is going to be denoted in that way. You'll notice that the modulus, the length of this vector squared, is still going to be x squared plus y squared, because you're going to get x squared plus minus y all squared, and minus y all squared, of course, is plus x plus y squared. So the modulus of z and the modulus of z star, or the complex conjugate of z, is always going to be x squared plus y squared. But I want to draw your attention to something rather interesting, which is that if you multiply z by its complex conjugate, you're going to get x plus iy multiplied by its complex conjugate x minus iy. And what you're going to get there is x squared. The plus iyx will cancel the minus iyx. And so you're now just going to be left with iy times minus iy, which is minus I squared y squared. But I squared is minus 1. So minus I squared is plus 1, and that will give you plus y squared. The complex number times its complex conjugate gives you the same result as the modulus of that number squared. The modulus of z squared was x squared plus y squared from Pythagoras, but you get the same result if you multiply the number by its complex conjugate. And that will be important when we get to some of the physics of quantum mechanics. I hope you will see that if z is just a real number, e.g. 2, then z star also equals 2, because you only change the imaginary term. You change the sign of the imaginary term. If you don't have an imaginary term, there's no sign to change. So the complex conjugate of a real number is just a real number. Now we need to consider what happens if we add these vectors. So let's say we've got a vector also on the complex plane. X remains the same, so the x dimension will be the same, but the imaginary term has changed signs. So now we're going to be at minus y, and consequently the vector z complex conjugate is going to be denoted in that way. You'll notice that the modulus, the length of this vector squared, is still going to be x squared plus y squared, because you're going to get x squared plus minus y all squared, and minus y all squared, of course, is plus x plus y squared. So the modulus of z and the modulus of z star, or the complex conjugate of z, is always going to be x squared plus y squared. But I want to draw your attention to something rather interesting, which is that if you multiply z by its complex conjugate, you're going to get x plus iy multiplied by its complex conjugate x minus iy. And what you're going to get there is x squared The plus iyx will cancel the minus iyx. And so you're now just going to be left with iy times minus iy, which is minus I squared y squared. But I squared is minus 1. So minus I squared is plus 1, and that will give you plus y squared. The complex number times its complex conjugate gives you the same result as the modulus of that number squared. The modulus of z squared was x squared plus y squared from Pythagoras, but you get the same result if you multiply the number by its complex conjugate. And that will be important when we get to some of the physics of quantum mechanics. I hope you will see that if z is just a real number, e.g. 2, then z star also equals 2, because you only change the imaginary term. You change the sign of the imaginary term. If you don't have an imaginary term, there's no sign to change. So the complex conjugate of a real number is just the real number. Now we need to consider what happens if we add these vectors. So let's say we've got a vector, this is a ket vector A, plus a ket vector B. That's going to produce a ket vector C. And the way it works quite simply, I'm going to use 3 dimensions to save a bit of time. So we're going to have A1, A2, A3, plus B1, B2, B3. What is that going to produce? Well, it couldn't be easier. It's going to be another ket vector, and you simply add the dimensions. So A1 plus B1 becomes the first term in the ket vector. A2 plus B2 becomes the second term, and A3 plus B3 becomes the third term. So this is one whole number because you've added these two together, so you get another ket vector with 3 dimensions. The important thing about all of this that you'll notice is that you must always use the same number of dimensions. It's no use adding a 3-dimensional ket vector to a 2-dimensional ket vector. That is not going to work. You always have to work in the same number of dimensions. I happen to choose 3 for illustration purposes. Now for very basic multiplication, let's say that we're going to take a number, which could be a complex number, multiplied by the ket vector A. We're going to see that that will produce another ket vector. And that, of course, is simply going to be alpha times, well, A, again, I can represent in 3 dimensions, A1, A2, A3. And that couldn't be easier. You simply multiply alpha on each of these terms to give you a new ket vector, which is alpha A1, alpha A2, alpha A3. So whatever that number, whether it's a real number or a complex number, you simply multiply each of the individual terms by that number, and that gets you the new ket vector C. Now we come on to what will turn out to be a very important concept when we get to the physics. And that is what happens if you multiply a bra vector by a ket vector. So we've got bra vector A times ket vector B. That is called an inner product. And it's kind of equivalent to a dot product if we were simply talking about ordinary vectors. And the way you work it out is you write out the bra vector, and you remember I said that the bra vector is a row vector where all the elements are complex conjugated, and we now know what that means, multiplied by the ket vector, which of course is a column vector, but this will be B1, B2, B3. And what that produces is not a vector, just a number. And the number is produced by taking the first element in each case and multiplying together, then adding the multiple or the product of this just a column vector, where all the way you work it out is you write out the bra vector, and you remember I said that the bra vector is a row vector where all the elements are complex conjugated, and we now know what that means, multiplied by the ket vector, which of course is a column vector, but this will be B1, B2, B3. And what that produces is not a vector, just a number. And the number is produced by taking the first element in each case and multiplying together, then adding the multiple or the product of the second elements, and then add the product of the third elements. I'll say that again. It's the product of the first elements, plus the product of the second elements, plus the product.
It's very similar, obviously, to vector algebra. I mean, it's called linear algebra, I'm sorry.
Of the third elements. So that will be A1 star times B1, plus A2 star times B2, plus A3 star times B3. That just becomes one number. It's a complex number, but it is just a number. It is not any longer a vector. Now, suppose I had asked us to do BA instead of AB. I think you will see that through kind of similarity, what you will get here is B1 star A1 plus B2 star A2 plus B3 star A3, because these will just be reversed.
But it's a different value, so it's not commutative.
If I now take BA and I complex conjugate it, I will get B1, because the complex conjugate of the complex conjugate gets you back to where you started, times A1 star, plus B2 times A2 star, plus B3 times A3 star. But that is the same as that, because the order of the numbers doesn't matter. And so we've just shown that AB is equal to BA complex conjugated. Now I must introduce you to a matrix. We're still doing the maths here. We haven't got on to any physics yet. I'm going to introduce you to a matrix. It's a square matrix. It can have any dimensions, but I'm going to choose 3 dimensions simply to make life easier. And a matrix you write with curly brackets, and it will have a row and a column. The rows M11, M12, M13, the second row M21, M22, M23, and the third row M31, M32, M33. And you'll notice that essentially I've got I rows and J columns, and each element can
Don't use I and J, Jesus.
be written as Mij. So if you take this element here, it's the second row, first column, so it's Mij, M21. Take this element here, it's the third row, it's the second column, M32. That's the way you actually identify the elements of the matrix. Each of those elements, each one of these values can be a complex number, and we know what that is. Now, I can create a complex conjugate of that matrix, which we call M star. And
This guy is the best teacher in the world. Hands down, by far. It's like there's no comparison.
guess how I do it? You're absolutely right. We simply take the complex
He just uses a marker and a paper and a camera. It's like the oldest method, and it's just the best.
conjugate of each element in the matrix. So I'm now going to write out each element, but for each one, I simply put a star, meaning that each element of the matrix has been complex conjugated. We know what that means. It means that the imaginary term changes sign. So here is the matrix. Here is the complex conjugate of the same matrix. In other words, Mij has become Mij star. And just to remind you again what that means, that if the complex number is x plus iy, then the complex conjugate becomes x minus iy. Now I'm going to introduce you to the transpose of the matrix. All you do here is you interchange rows and columns. The diagonals stay the same, but the matrix essentially flips over. So the rows become columns and the columns become rows. So MT now becomes M11, M21, M31, as opposed to, you'll notice it was M11, M12, M13. It's now the other way round. Then this becomes M12, M22, M32, and this becomes M13, M23, M33. That's what's called a transposed matrix, or if you like, the more general term is to say that Mij has become Mji. You've just interchanged the rows with the columns. You'll notice, however, that the diagonals remain the same, M11, M22, M33, M11, M22, M33. But these two numbers have interchanged. They transpose positions. Those two numbers have transposed. Those two numbers have transposed. It's a kind of mirror image about the diagonal. Well, now I must introduce you to another matrix, which is called M dagger. And that is a combination of these two. It's both a complex conjugate and a transpose. So first of all, we have to take the transposed matrix, which is M11, M21, M31, M12, M22, M term. And we know what that means. 3, 3, that's the transposed matrix, that's just that. And now we complex conjugate every term. And we know what that means. So that is now what's called the complex conjugate of the transpose, which we represent as M dagger. So in other words, what's happened here is Mij of our original matrix has become Mji complex conjugated. And now we consider a situation where M, the matrix, equals M dagger. And let me give you an illustration. If M is equal to, and I'm only going to do a two-dimensional matrix here to save time. This is the matrix. It's got 4 elements, 2 rows.
What? The original matrix is equal to the M dagger?
There's 2 columns, 1, 1 plus I, 1 minus I, and 3. What is M dagger? Well, remember, M dagger, you have to transpose about the diagonal and complex conjugate. The diagonal doesn't change. So the 2 elements of the diagonal don't change, and anyway, they are not complex numbers. 1 plus I has to move down to here, but it also has to be complex conjugated, so it becomes 1 minus I. The 1 minus I has to go up to here, but it has to be complex conjugated, so it becomes 1 plus I. And you'll notice that M equals M dagger. When that happens, the matrix is called Hermitian. That means that the matrix is equal to its transposed complex conjugate. I'm afraid we need to continue with the maths a little further.
Oh, it's a special case.
Now we want to ask what happens to the 1 plus and 1 plus the matrix, the complex conjugate of the trig I, complex conjugated. And now we consider a situation where M, the matrix, equals M dagger.
It's just a situation.
Give you an illustration. Dagger, you don't change, and it's I. When that happens, conjugate. I'm afraid we need to continue with the maths a little further, because now we want to ask what happens if we have a matrix and we apply it to a ket vector. Well, we can write that out. I'm going to do this in 2 dimensions to save time. So M11, M12, M21, M22. That's the matrix. The vector is A1, A.
It's even, I mean, it's called the matrix, just like in linear algebra.
2. And if you multiply that out, you will get another ket vector. That's the key point. And the way you get it is you take this number times that number plus that number times that number. That's the top.
That's exactly like in linear algebra.
Line. And then this number times this number plus this number times that number is the bottom line. I'll do that again. This number times this number plus this number times that number is M11 times A1 plus M12 times A2. That's the top. That's all just one number. So that's the top of our new ket vector. And this one is that number times that number, which is M21 A1 plus this number times this number, M22 times A2. And that's a new ket vector because there's just one number at the top, one number at the bottom. This is just an addition of 2 very likely complex numbers. But nonetheless, what essentially you've got from the action of a matrix on a ket vector is just a new ket vector. I need to introduce you to what is called the identity matrix. And the reason it's called an identity matrix is that it has numbers 1 on the diagonals and 0s everywhere else. So I'm going to do a 3-dimensional matrix, but you'll easily see how to create any dimensions. The diagonals have 1s, everything else is 0. And that is called the identity matrix, or sometimes called the unit matrix. Not to be confused with the unitary matrix, which has the following properties, that if you take the unitary matrix and multiply it by U dagger, which you will remember is the transposed complex conjugate of U, that gives you the identity matrix. In other words, you can consider that U dagger is the inverse of U. So when you multiply U by U dagger, you essentially get the identity matrix. Then I need to explain to you what a determinant is. If we want the determinant of matrix M, we write that determinant of matrix M, identity matrix, in U dagger. The unitary matrix, which has the following properties, that if you take the unitary matrix and multiply it by U dagger, which you will remember is the transposed complex conjugate of U, that gives you the identity matrix. In other words, you can consider that U dagger is the inverse of U. So when you multiply U by U dagger, you essentially get the identity matrix. Then I need to explain to you what a determinant is. If we want the determinant of matrix M, we write...
This is literally vector algebra. I mean, linear algebra.
That with straight lines rather than with curly brackets. And if the matrix is made, I'm going to do a 2x2 matrix, A, B, C, D, where A, B, C, and D will all be complex numbers. The way you calculate the determinant is it's A multiplied by D minus B times C. For 3 dimensions, it's a little bit more complicated, but we're not going to need that for the time being. So let's just stick with 2. You multiply the 2 terms on the diagonal and subtract the product of the 2 terms on the off diagonal. And you can see immediately that the determinant of the identity matrix, which of course would in this case be 1, 0, 0, 1, would be 1 times 1 minus 0 times 0. The determinant of the identity matrix is 1. Now I need to introduce you to the trace of a matrix. And the trace of a matrix, if the matrix is A, B, C, D, then the trace of the matrix couldn't be easier. It's just the sum of the elements on the main diagonal. So in this case, it will be A plus D. If it were a 3 by 3 matrix, you just add all the numbers on the main diagonal, and that is called the trace. And you'll be delighted to know that we've almost come to the end of the notation and the mathematics, and we'll soon get on to the physics. There's just one more thing to explain, so bear with us. You'll remember that we showed a thing called a Hermitian matrix. That was when the matrix equals its transposed complex conjugate. And where you've got a Hermitian matrix, which I will represent with the sign H, you can act on a vector, a ket vector, A, to produce the self-same vector A, but multiplied by a number, not a vector, not a matrix, just a number. It might be a complex number, but in this case, it will be a real number. So it'll have no complex, it'll have no imaginary term. And that is going to prove to be one of the most important equations in the whole of our quantum mechanics dealings. So what we're saying in maths terms is that a Hermitian matrix acting on a vector produces the same vector, but now just multiplied by an ordinary real number. And when that is the case, that vector is called an eigenvector, and that number is called an eigenvalue. What you will typically find is that that self-same Hermitian matrix may operate on a different vector to produce the same different vector, but multiplied by a different real number. And what you will say is that for each Hermitian matrix, they will have 2 separate eigenvectors, each of which will give rise to a separate eigenvalue. That's the maths. Now we can move on to the physics. And what the physics says is that the Hermitian matrix represents a measurable or an observable, something that you're going to actually measure. It says it will give rise that for each, what you vector is called an eigenvector, and that number is called an eigenvalue. What you will typically find is that that self-same Hermitian matrix may operate on a different vector to produce the same different vector, but multiplied by a different real number. And what you will say is that for each Hermitian matrix, they will have 2 separate eigenvectors, each of which will give rise to a separate eigenvalue. That's the maths. Now we can move on to the physics. And what the physics says is that the Hermitian matrix represents a measurable or an observable, something that you're going to actually measure. The eigenvectors represent the possible states of the system, and the eigenvalues represent the actual results you get when you make the measurement. I hope all will become clear when I do some examples of this in a moment. I want to consider some of this by considering the issue of polarization. Now, we covered that in one of the videos in the series on electromagnetic radiation. And amongst other things, we said that if you take unpolarized light and you send it through a polarizer, which will polarize vertically, that's how I will represent a polarizer that will polarize vertically. You send unpolarized light through this polarizer. When it comes out the other side, it will be vertically polarized. If you then send it through another polarizer, which is also vertically polarized, then all of the light in this section will get through. 100% of the light that is polarized gets through the vertical polarizer and comes out the other side, because the polarizer is in the same direction as the light that is polarized. It all goes through. By contrast, if we take exactly the same experimental setup with our vertical polarizer, and we send it through a polarizer, this is now polarized in the vertical direction, we now send it through a polarizer that is horizontal, then absolutely nothing gets through. This is experimentally verifiable. You've got polarized light in vertical direction. Will it go through a horizontal polarizer? Not at all. And then the final example we just use is that you take unpolarized light, you put it through the vertical polarizer, out it comes vertically polarized, and now you put it through a polarizer which is polarized at 45 degrees. And what do you find? You find that 50% of the intensity of the light that was coming towards this polarizer comes out the other side. So whatever the intensity is of the polarized light here, 50% of it comes out the other side. That's what we learned from the video on electromagnetic radiation. That is all experimentally verifiable. More generally, we said that if you put this light through a polarizer in the vertical direction, so that it comes out vertically polarized, and then you then put it through a polarizer which is at an angle theta to the vertical direction, then the intensity of the radiation that comes through that second polarizer will fall off according to cos squared theta. In other words, when theta is 0, that is to say the polarizer is in exactly the same direction as the original polarizer and the polarized light. When cosine theta is 0, when cosine 0 equals 1, when theta is 0, cosine theta is 1, cosine squared theta is 1, 100% of the light comes through. When theta is 90, cosine 90 is 0, cosine squared 0 is 0, none of it comes through. So the intensity of the radiation falls off according to the angle between this polarizer and this polarizer. But I said that there was a bit of a problem with this in terms of dealing with it solely classically mechanical, because the intensity of radiation is proportional to the E field squared. And this might be taken to suggest that if the intensity falls off
To the E field squared? What is the E field squared?
intensity of radiation is proportional to the E field squared. And this might be taken to suggest that if the intensity falls off as the cosine squared term, if intensity goes down squared, dealing with it solely classically mechanical, because the intensity of radiation is proportional to the E field squared. And this might be taken to suggest that if the intensity falls off as the cosine squared term, if intensity goes down, that must mean that the E field goes down. And that means that the total...
What is the E field? The electric field? What?
energy goes down. Now, the total energy, you know that the energy of a photon is given by Planck's constant times the frequency. So that suggests that if the energy is going down, since h is a constant, the frequency must be going down. And that suggests that the light will change color. But in fact, that's not true. What happens is if you send blue light, polarized here, less blue light will go through. The intensity of the blue light will change by cosine squared theta, but the color won't change.
I'm gonna go get more gum. 3141.
So this can't be entirely right. And what we're now going to look at is the quantum mechanical concept, which says, and I'll just give you a brief overview, what happens is that this unpolarized light consists of lots of photons. Some of them will get through this first polarizer, and some of them won't. The ones that get through will be polarized vertically. When the photons get to the next polarizer, again, some of them will get through, some of them won't. The ones that do get through retain the same frequency of the radiation. It's just that fewer of them get through. Consequently, the total intensity reduces because the total number of photons that gets through reduces. So the total amount of energy that gets through reduces because each photon contains a certain amount of energy. And if fewer of them get through the second polarizer, then there will be less energy overall that gets through, but the frequency of the radiation doesn't change. Now we're going to look at that from a quantum mechanical point of view using the concepts that we developed earlier in this video. And if you, again, I say, if you ask me the question, why do we do that? The answer is because it works. So I'm going to consider polarization horizontally as being the x state represented as the x het vector. And I'm going to call that 1, 0. Now, I'm conscious that I haven't explained why I've done that. That will come later. For the time being, let's just get some general concepts out so you can see how it works. I'm also going to consider vertical polarization, and I'm going to call that the y het vector, and that is going to be represented as 0 and 1. Now I'm going to introduce that term that I said would be very important, and that is the inner product of x and y. And this turns out to have a very important physics meaning. But for the time, and you do that quantita, you see here, less blue light will go through. The intensity of the blue light will change. But in fact, that's not true. What happens is if you send blue light polarized here, less blue light will go through. The intensity of the blue light will change by cosine squared theta to the E field squared. And this might be taken to suggest that if the intensity falls off as the cosine squared term, if intensity goes down, that must mean that the E field goes down. And that means that the total energy goes down. Now, the total energy, you know that the energy of a photon is given by Planck's constant times the frequency. So that suggests that if the energy is going down, since h is a constant, the frequency must be going down. And that suggests that the light will change color. But in fact, that's not true. What happens is if you send blue light polarized here, less blue light will go through. The intensity of the blue light will change by cosine squared theta, but the color won't change. So this can't be entirely right. And what we're now going to look at is the quantum mechanical concept, which says, and I'll just give you a brief overview, what happens is that this unpolarized light consists of lots of photons. Some of them will get through this first polarizer, and some of them won't. The ones that get through will be polarized vertically. When the photons get to the next polarizer, again, some of them will get through, some of them won't. The ones that do get through retain the same frequency of the radiation. It's just that fewer of them get through. Consequently, the total intensity reduces because the total number of photons that gets through reduces. So the total amount of energy that gets through reduces because each photon contains a certain amount of energy. And if fewer of them get through the second polarizer, then there will be less energy overall that gets through, but the frequency of the radiation doesn't change. Now we're going to look at that from a quantum mechanical point of view using the concepts that we developed earlier in this video. And if you, again, I say, if you ask me the question, why do we do that? The answer is because it works. So I'm going to consider polarization horizontally as being the x state represented as the x het vector. And I'm going to call that 1, 0. Now, I'm conscious that I haven't explained why I've done that. That will come later. For the time being, let's just get some general concepts out so you can see how it works. I'm also going to consider vertical polarization, and I'm going to call that the y het vector, and that is going to be represented as 0 and 1. Now I'm going to introduce that term that I said would be very important, and that is the inner product of x and y. And this turns out to have a very important physics meaning. What it means is, if I prepare light in the y state, that is to say, I prepare it in the vertically polarized state, what are the chances of it going through an x polarizer, that is, a horizontal polarizer? Now, we already know the answer to that. If you prepare it in the vertical state and try and bring it to a horizontal polarizer, nothing
0.
will get through. So we know the answer experimentally, and we know the answer classically. So this has got to come up with the same result. And what we say in physics is that the inner product of x with y, that is, you prepare it in y and you try to put it through x, that whole term is what is called the probability amplitude. Not the probability yet, it's the probability amplitude. To get the probability, you have to square it. Or to be absolutely precise, you have to take the probability amplitude and multiply it by its complex conjugate. Remember, we showed that yx is the complex conjugate of xy. Now, as it happens, you'll notice that there are no complex numbers in these vectors. So for the time being, at least, this nuance will not be a worry to us. All we need to do is to take the inner product and square it, and we get the probability. Why is this inner product the probability amplitude? And why is the square of the probability amplitude the probability? There is no way of proving that. That was a quantum mechanics principle or a concept. I think it was developed by Max Born, who simply asserted it. And the point is, it actually accords with experiment, and that's why we use it. So this is a very important term. As I said, you prepare in y and you try and put it through x. And we know the answer must be 0 because there's no chance of a photon that is vertically polarized going through a horizontal polarizer. So let's see if that works. So how do you take x, inner product of x with y? Well, you take x and you make that a row vector, so that's 1, 0. You should actually complex conjugate it, of course, but there is no imaginary number, so there's nothing to do. And then you multiply it by the y vector as a column vector. And you know what the rule is? It's that times that plus that times that. So it's 1 times 0 is 0, plus 0 times 1 is 0, gives you the answer 0. And of course, you now need to square it. So 0 squared is 0. So the probability of a photon prepared in the y axis, which is the vertical axis, going through a horizontal polarizer is 0. So far, it works. Well, let's do a few more tests. Suppose you prepare it in the x frame and you send it through an x polarizer. That is to say, you polarize it in the horizontal direction and you send it through a horizontal polarizer. Well, that's kind of the equivalent of this here, except that these are two verticals. If they're both horizontal, the light will go through, 100% will go through. The probability will be 1. Is that true? Obviously, remember, to get the probability, we need to do the square. So that's going to be, well, x is 1 naught. So that's going to be 1 naught times 1 naught. This should be complex conjugated. I will keep saying this, but there's nothing
But how do you know x is 1 naught?
to do a complex conjugate because there's no complex number. So now you get 1 times 1, which is 1, plus 0 times 0, which is 0. 1 plus 0 equals 1. 1 squared is 1. And so we've shown that if you prepare in the x or the horizontal polarization and you try and put it through a horizontal polarizer, 100% will go through. Well, let's for completeness just check that the other one works. If you prepare it vertically and try and get it to a vertical polarizer, what's the probability of it going through? Well, we know the answer. That's 100%. Will it work? Well, what is the y? Is 0, 1. So this is going to be 0, 1, which I'll say again should be complex conjugated, but there's nothing to do, times 0, 1. 0 times 0 is 0, plus 1 times 1 is 1. That gives you 1. 1 squared equals 1. 100% of photons prepared in the y frame, which is the vertical polarization, will go through a vertical polarizer. And if we look again at this equation, where we did the inner product of x with y, and we got 0, that is no chance of anything in the y, that is the vertical polarization, going through a horizontal polarizer. What we are saying, if you get a result 0, you can say that x and y are what is called orthogonal. That is to say, they are completely inconsistent. If it's in y, it definitely won't go through x. If it's in x, it definitely won't go through y. Now I want to remind you about another equation that we developed that I said would prove to be very important, and that was a Hermitian matrix acting on a vector A gives exactly the same vector A multiplied by a real number, where that number is not the matrix, it's not a vector, it's just a number. And I said that you could assign physical meanings to these. H, the Hermitian matrix, becomes the operator or the measurable or the observable, the experiment if you like. The eigenvector is the state the system can be in, and lambda is the result that you get. So let's say that I have an experiment which I will call.
So this is just a shorthand of the results of the experiments.
H, and I'll put a little circle there, which means what I'm about to measure is either the
experiments make sense. I mean, what's the purpose of all this shorthand? I mean, it's okay, but fine, right?
Vertical or the horizontal polarization of a photon. For the time being, we're going to ignore all other directions, and lambda is the result that you get. So let's say that I have an experiment, which I will call H, and I'll put a little circle there, which means what I'm about to measure is either the vertical or the horizontal polarization of a photon. For the time being, we're going to ignore all other directions. It's either horizontal or it's vertical. And I'm going to act on the x eigenvector.
X is 1, 0, whatever that means.
Remember that x was the horizontal polarization, and we represented it, I'll just put it over here, we represented that as 1 naught. I didn't tell you why, that will come later. Now, what I'm asserting is that if you've got a Hermitian matrix acting on a vector, you will get the same vector multiplied by a number. So we expect to get a number multiplied by x. And the question is, do we do so? Well, I will need to tell you.
We never proved it.
What this matrix is. Again, I'm going to tell you, I'm not going to derive it, but we will illustrate the derivation of it later on. For the time being, I'm just going to tell you that we can represent this Hermitian matrix, which is the operator or the measurable, as it's a 2 by 2 matrix, and it couldn't be simpler. Well, I suppose it could, but not by much. That is the Hermitian matrix, which is the vertical or horizontal measurement. So what I've got to do is to apply this to the x eigenvector and see if I get the same eigenvector with a number in front of it. Well, let's see.
You apply it to the x vector. That's an eigenvector, I guess.
So we've got 1, 0, 0, minus 1. That is the Hermitian matrix, the operator, acting on x. And x is 1, 0. And now you've got to remember your matrix times vector multiplication rules. It's 1 times 1 plus 0 times 0 is the top number. Well, 1 times 1 plus 0 times 0 is 1. And then for the bottom number, it's 0 times 1 plus minus 1 times 0. Well, 0 times 1 is 0, minus 1 times 0 is 0. That's 0. That vector and that vector are exactly the same, which is what we expect to get here. What is the number in front? It is simply plus 1. It is a number, it is a real number, it is simply plus 1. So we've taken this general term here, where we've got eigenvectors and eigenvalues, and we've shown that if we use this operator, which is the measurable, and we apply it to the x eigenvector, which is represented like this is the horizontal state, you get plus 1 times the original state. Now let's see what happens if we apply it. This is the self-same operator, so we're still going to use this matrix.
570,000 views, 500 billion views, 752 comments. That's a lot of comments, my God. He is so efficient. He teaches so fast. Anyway, 44.3. Let me go get more gum.
But we're now going to apply it to the y vector, and we should get lambda, a different lambda, of course, now, times the y state. Or do we? Well, here we go again. H, the Hermitian matrix, is once again 1, 0, 0, minus 1. But this time, y, you may remember, is 0, 1. That's what I gave you. That's the vertical. That's the state representation of the vertically polarized photon. Well, what does that give us? Again, it's going to give us a vector. You take 1 times 0 plus 0 times 1. Well, that's 0. And then you take 0 times 0 plus minus 1 times 1, that's minus 1. And that is not equal to that. But I can quickly make it equal to that. I just put minus 1 in front, and then I convert that to plus 1. And then minus 1 times 0 is 0, minus 1 times 1 is minus 1. So effectively, I've now got exactly the same eigenvectors here, but the number in front is now minus 1. So I've got a situation that when I apply this matrix, this measurable, this experiment, onto the x eigenvector, which is the horizontal, I get an eigenvalue of plus 1. When I apply the same observable onto the y eigenvector, I get the same eigenvector back, but with an eigenvalue of minus 1. So if you like, h is the observable, and the only observable is this photon, or is this beam of light polarized vertically, or is it polarized horizontally? The states for horizontal and vertical polarization are given like this, and the result of the experiment, is it horizontal or is it vertical, are given by the eigenvalues plus 1 or minus 1. And you could look at it like this. You could have an experiment, sort of a kit, a piece of kit. We don't know what's inside that piece of kit, but it tests to see whether light is vertically or horizontally polarized. I mean, the best way of doing it, of course, is simply to have a vertical polarizer. And then if the light goes through it, and behind it you have, say, a light-sensitive diode or some light-sensitive device. And if the light goes through it, since it can only, for the time being, the conditions are it can either be vertically polarized or horizontally polarized. If the light that hits this polarizer goes through, it must be vertically polarized. If it doesn't go through, it must be.
Okay. We were, I remember. So we discovered that it was one. Basically, we were here.
Eigenvector, which is a that times 1 times 1 plus minus 1 times 0, or 0 times 1 is 0, minus 1 times 0 is 0, that's 0. That vector and that vector are exactly the same, which is what we expect to get here. What is the number in front? It is simply plus 1. It is a number, it is a real number, it is simply plus 1. So we've taken this general term here, where we've got eigenvectors and eigenvalues, and we've shown that if we use this operator, which is the measurable, and we apply it to the x eigenvector, which is represented like this is the horizontal state, you get plus 1 times the original state. Now let's see what happens if we apply it. This is the self-same operator, so we're still going to use this matrix, but we're now going to apply it to the y vector, and we should get lambda, a different lambda of course now, times the y state. Or do we? Well, here we go again. H, the emission matrix, is once again 1, 0, 1, but this time y, you may remember, is 0, 1. That's what I gave you. That's the vertical, that's the state representation of the
So I'm beginning to understand the notation. I'm not saying I see the usefulness. It's a shorthand of experimentation, and it's interesting.
vertically polarized photon. Well, what does that give us? Again, it's going to give us a vector. You take 1 times 0 plus 0 times 1, well, that's 0. And then you take 0 times 0 plus minus 1 times 1, that's minus 1. And that is not equal to that. But I can quickly make it equal to that. I just put minus 1 in front, and then I convert that to plus 1. And then minus 1 times 0 is 0, minus 1 times 1 is minus 1. So effectively, I've now got exactly the same eigenvectors here, but the number in front is now minus 1. So I've got a situation that when I apply this matrix, this measurable, this experiment, onto the x eigenvector, which is the horizontal, I get an eigenvalue of plus 1. When I apply the same observable onto the y eigenvector, I get the same eigenvector back, but with an eigenvalue of minus 1. So if you like, h is the observable, and the only observable is this photon, or is this beam of light polarized vertically, or is it polarized horizontally? The states for horizontal and vertical polarization are given like this, and the result of the experiment, is it horizontal or is it vertical, are given by the eigenvalues plus 1 or minus 1. And you could look at it like this. You could have an experiment, sort of a kit, a piece of kit. We don't know what's inside that piece of kit, but it tests to see whether light is vertically or horizontally polarized. I mean, the best way of doing it, of course, is simply to have a vertical polarizer. And then if the light goes through it, and behind it you would have, say, a light-sensitive diode or some light-sensitive device. And if the light goes through it, since it can only, for the time being, the conditions are it can either be vertically polarized or horizontally polarized. If the light that hits this polarizer goes through, it must be vertically polarized. If it doesn't go through, it must be horizontally polarized. And what we can do on this piece of equipment, we can have two lights, a red light and a green light. And the red light comes on if the light goes through the polarizer, which means it must be vertically polarized. And the green light comes on if the light doesn't go through the vertical polarizer, which means it must be horizontally polarized, because those are the only two directions that at the moment I'm allowing. So if you like, the piece of equipment, which is the measurable, is H. The states of the light coming in, that is these eigenvectors here, represent whether the light is actually vertically polarized or horizontally polarized. And the eigenvalues, which are plus 1 or minus 1, are really just, does the red light come on or does the green light come on? They are different. And it's the red light and the green light which are the true results of the experiment. You cannot measure H. You cannot directly measure the state. The only thing you can do is to look at the result. Did the red light come on? Did the green light come on? And they are represented by the eigenvalues. And I've prepared this little chart here, which I shall flash up from time to time to remind us of where we're coming from. This is the basic equation. The Hermitian acting on an eigenvector produces a number multiplied by the same eigenvector. Above this, I've written down what the mathematics says. You've got a Hermitian matrix acting on an eigenvector. It produces the same eigenvector and a real eigenvalue. Below, I've put what that means in the physics. In the physics, H represents the observable or the measurable, the experiment. A represents the possible state of the system. There will always be two or more, otherwise the thing becomes trivial. In the example I've just given you, there were two, vertical or horizontal. that will produce the same state, but multiplied by a number, and that number will change depending on whether the system is vertically or horizontally polarized. And indeed, that number is represented by the experiment as whether the red light or the green light comes on. So this representation of quantum mechanics has worked so far, but we've got a lot further to go. So now let's do a little bit more of a test. This time I'm going to take unpolarized light and send it through a vertical polarizer. So of course it will come out vertically polarized, there's no question about that. And now I'm going to send it through a second polarizer, which is at the 45-degree angle, and it's the / 45-degree angle. And the question is, what will come out the other side? Well, classical mechanics already tells us this. Whatever the intensity is of the light that is in the vertically polarized state here, it will be half of that comes through. The more general case, as we showed, was it's cos squared theta. In this case, theta is 45 degrees. The cosine of 45 degrees is 1 over root 2. Cos squared theta is 1 over root 2 squared, which is a half. So classically, we already know the answer. Whatever the intensity of the polarized light, what we'll get through the polarizer, which is at an angle of 45 degrees, is half of that intensity. And here we can pause and wonder at the weirdness of quantum mechanics, because what we're actually saying in quantum mechanics terms is that this polarized light consists of photons. If this is monochromatic light, that is, it's all the same color, say red light, all those photons will have the same energy, because we know that the energy of a photon is h times the frequency, and if the frequency is common because it's the same color, red, then all the photons have the same frequency. All the photons are polarized vertically, so all those photons are absolutely identical. And here's the weirdness of quantum mechanics. When they get to this polarizer, half of them will go through and half of them won't. And there's absolutely no way of telling which half will and which half won't. You can only say that there's a probability that any photon arriving at that polarizer has a 50% chance of getting through. 50% of them will, 50% of them won't. And the only thing you can say about that is that that is weird. But having accepted that it's weird, we now need to work out what the
So there's no mechanical model to explain why this happens?
representation of a / 45-degree state is. We've already said that we've got the x state, which is the, remember, horizontal state, and we said we have a y state, which is the vertical state. So you might think that we can represent the state, which I'll put like this, the Keck vector of the 45-degree / state. You might think that you could represent that as simply a combination of the x state and the y state, because of course it's got a bit of both. It's got an upward, it's got a vertical dimension, and it's got a horizontal dimension. So it could be just the combination of the two. But I will show you that that is not going to quite work. It's not far short, but it's not going to work. Why is it not going to work? Well, let's just work out what that would mean. The x component, remember, was 1, 0, and the y component was 0, 1. And I told you how to add vectors. You just add the two top numbers and the two bottom numbers. So that would give you a representation of 1, 1. Nothing wrong with that, you might say. But I now ask the question, what is the probability if I prepare my photon in the 45-degree angle polarization? What is the probability of it going through a 45-degree angle polarizer? And we all know the answer to that. It must be 100%. If you prepare it polarized in that direction, it will go through, certainly, a polarizer polarized in that direction. So remember, that's the probability amplitude. To get the probability, we have to take the square. So let's see what that amounts to. Remember, we just assumed, as it turns out it'll be wrong, but we've assumed that the / state can be represented as a 1, 1 vector. Well, to do the inner product, we have to do 1, 1 multiplied by 1, 1. That's 1 times 1 plus 1 times 1 is 2, but we have to square it, and that gives us 4. So there's a 400% chance that a photon produced in the 45-degree / direction will go through a / polarizer. You cannot have a 400% chance. It can only be a 100% chance. So we have to do what's called normalize. We have to adjust this so that when we do this calculation here, we get 1 instead of 4. And the trick is that you simply make the / state equal to x divided by the square root of 2 plus y divided by the square root of 2. And if you use x and y divided by root 2 in each case, then this will become 1 over root 2 naught, this will become naught and 1 over root 2, and when you put that into this equation, you will get the number 1. It's called normalizing. It just ensures that whenever you do the inner product of identical vectors, you get 1 and not the absurd answer 4. Okay, so just to recap, we have established that the / state can be represented as x plus y divided by the square root of 2, where remember x was simply given as 1 naught, and y is given as naught 1. So in other words, x over root 2 will mean that you've got a 1 over root 2 and a naught, and y over root 2 will mean you've got a naught and 1 over root 2. So the next question is, what then is a 45-degree angle polarizer that's a backslash at 45 degrees? And let's take a guess.
The reason why he's so easy to understand is because he never skips steps. He hardly ever skips steps. He's like very, very step by step. Everything is step by step. No skipping steps. Once you don't skip steps, everything becomes really straightforward. It's all you need to do is just remember. But the derivations are trivial.
Turns out to be right, that it is x minus y over root 2. And if you substitute these two in, if you do the inner product to be right, what then you've got x identical. And when you put that into this equation, you will get the number 1. It's called normalizing. It just ensures that whenever you do the inner product of identical vectors, you get 1 and not the absurd answer 4. Okay, so just to recap, we have established that the / state can be represented as x plus y divided by the square root of 2, where remember x was simply given as 1 naught, and y is given as naught 1. So in other words, x over root 2 will mean that you've got a 1 over root 2 and a 0, and y over root 2 will mean you've got a 0 and 1 over root 2. So the next question is, what then is a 45-degree angle polarizer that's a backslash at 45 degrees? And let's take a guess, which turns out to be right, that it is x minus y over root 2. And if you substitute these two in, if you do the inner product of backslash with backslash, you will indeed get 1, which of course is the acid test that this will work. So let's just calculate what the actual vectors are going to be in their matrix, sorry, in their sort of column vector form. The forward slash.
Which means it's 100%. We would need to go through it, but I'm too tired.
Slash is going to be x over root 2, which is 1 over root 2 naught. Right, from this is x over root 2 is 1 over root 2 naught, and the y is going to be naught and 1 over root 2. And remember, the addition is you just add the two top numbers and you add the two bottom numbers, so that's going to give you 1 over root 2 and 1 over root 2. So the vector representation for a forward slash is 1 over root 2 and 1 over root 2. If you want the backslash, well, we've already shown what that is. It's 1 over root 2 bottom numbers, root 2, the forward slash. Forward slash is going to be x over root 2, which is 1 over root 2 naught. Right, from this is x over root 2 is 1 over root 2 naught, and the y is going to be naught and 1 over root 2. And remember, the addition is you just add the two top numbers and you add the two bottom numbers, so that's going to give you 1 over root 2 and 1 over root 2. So the vector representation for a forward slash is 1 over root 2 and 1 over root 2. If you want the backslash, well, we've already shown what that is. It's x minus y over root 2. X is going to be 1 over root 2 and naught, minus now naught 1 over root 2. So that's going to be 1 over root 2 minus naught is 1 over root 2. Naught minus 1 over root 2 is minus 1 over root 2. So the column vector representation of the backslash at 45 degrees is 1 over root 2 and minus 1 over root 2. So now we better do the acid test and see if quantum mechanics is going to succeed. What is the probability? If I prepare the photon in the forward slash state, what is the probability that it will go through a polarizer in the backslash state? Now, those two polarizers
should be 0.
Are at 90 degrees. So we know the answer. Nothing will go through. Consequently, the probability amplitude, which is this, and the probability itself, which will be the square of this, must be 0. That's what we've got to hope for. Okay, let's see if it is. What is the backslash? Well, backslash is this term here, and we put it as a column vector. 1 over root 2 minus 1 over root 2. It should be, I'll keep saying this, it should be complex conjugated, but there's no I terms, so there's no imaginary terms to complex conjugate. Get about that. Multiply by, or taking the inner product with the forward slash, which is this one. 1 over root 2, 1 over root 2. And how do we calculate that? We take that times that plus that times that. Well, 1 over root 2 times 1 over root 2 is a half, minus 1 over root 2 times 1 over root 2 is minus a half. That equals 0. And of course, we have to square it. It still equals 0. Quantum mechanics is still working. The probability of preparing a photon in a forward slash position at 45 degrees.
It's not that quantum mechanics is working. It's that this mathematical protocol that you have invented is a good model for the experiments that we have conducted.
And getting it through a backslash at 45 degrees polarizer remains at 0, which is what we expect. And we've already shown that if you prepare it in a forward slash and you try and put it through a forward slash, it will be 100% of the time. Okay, so let's see if we can test it a little bit further. We take our unpolarized light and we put it through a vertically polarized polarizer. It comes out, it's vertically polarized, of course, and now we put it through a forward slash polarizer. And the question is, what proportion will go through? What's the probability the photons will go through? We already know from classical mechanics.
Half.
X, 50%. Now we ought to be able to do it with our inner product. So what's our inner product? Remember, you prepare it on the right, and you test to see if it will go through on the left. That, of course, is what's called the probability amplitude, and to find the actual probability, you have to square it. And that should come to a half, which, of course, is the equivalent of 50%. So that will be equal to, well, the forward slash, remember, was represent
1 0. Oh, slash, yeah. 1 over square root of 2, 1 over
it is 1 over root 2, 1 over root 2, and that has to be in row form. So 1 over root 2, 1 over root 2, multiplied by.
Oh, that's 1 0.
The vertical vector, and remember the vertical vector was represented as.
Vertical is 0, 1? Or you have to transpose it? You have to do something to it?
1. So let's do the calculation. And what do we get? 1 over root 2 times 0 is 0, plus 1 over root 2 times 1 is 1 over root 2. But we have to square it. And 1 over root 2 squared is a half. Yet again, the formalism is working. We have worked out the probability of preparing in the vertical case and try and get it through an polarizer which is angled at 45 degrees. We know classically there's a 50% chance, or at least 50% of the intensity gets through. Quantum mechanics tells us that there is a half, which equates to 50% of the probability of a photon prepared in that state getting through a polarizer in this state. Now I need to tell you the Hamiltonian for the two types of forward slash backslash.
Did he just say Hamiltonian? Isn't the Hermitian?
Now I need to tell you the Hamiltonian for
Oops, I meant the Hermitian.
Or the two types of forward slash backslash. Those are the two options now. And the Hamiltonian is given, I'll give it to you, I'll show you why in a future video, is actually 0, 1, 1, 0. So once again, we've got that famous equation, which I prepared here, that the Hamiltonian times the eigenvector is equal to number times the eigenvector. So when we take this Hamiltonian and multiply it by a state, we're going to get a number multiplied by the state. So let's try it. The Hamiltonian, I told you, is 0, 1, 1, 0. Now I'm going to apply this to the forward slash. And the forward slash is
1 over root 2, 1 over root 2.
Is 1 over root 2, 1 over root 2. And that is going to give me
0, 1 over root 2. 1 over root 2 is 0. I mean, it's 0, 1 over root 2. So it's just 1 over root 2. And 1 over root 2 is 0. So it's just 1 over root. So it's 1 over root 2, 1 over root 2. So it's the same.
another vector. Well, what vector does it give it?
Which means the eigenvalue is +1.
So to get the top number, it's 0 times 1 over root 2 plus 1 times 1 over root 2, which is 1 over root 2. And the bottom number is 1 times 1 over root 2 plus 0 times 1 over root 2, which is 1 over root 2. Those two are the same, and the number, once again, is +1. And let's do it the other way. Let's take the Hermitian matrix for the forward and backslash measurements. This time we'll apply it to the backslash, which you'll remember was
1 over root 2, negative 1 over root 2.
1 over root 2 minus 1 over root 2. That's going to come to...
So it's 0 or negative. So it's negative 1 over root 2. And then 1 over root 2. So the number is negative 1.
0 times 1 over root 2 plus 1 times minus 1 over root 2 is minus 1 over root 2. 1 times 1 over root 2 plus 0 times minus 1 over root 2 is plus 1 over root 2. That is not equal to that. But I can very easily make it equal to that simply putting a minus 1 in front and then multiplying this by minus. So the minus becomes a plus and this by minus. And now you've got that that is the same as that. But the eigenvalue is minus 1. This is the equivalent of my red light and my green light. I take my piece of equipment, which is my, as it were, measurable. I apply it to one of two different states. If it's this state, you get a +1, which means the red light comes on. If you get this state, you get a -1, which means the green light comes on.
So the eigenvalue is the actual measurement.
We'll continue with more examples of this in the next video. This may seem a very complicated way of stating the very obvious. Indeed, we could have done virtually all of this using classical mechanics, and it would have been easier too. But as we shall see, it's a very powerful way of describing quantum states and outcomes which, and this is the key point, are probabilistic rather than deterministic. Hello, today we are continuing in our series on quantum mechanics concepts.
Very nice. Mm-hmm. 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 Did they leave me a message? There's no way to know. Actually. Mm-hmm.
There he is. Yeah, Mr. Slave.
Hey, what's up?
So what? Okay. Is it possible, and I pulled you in here for a very important reason,
Mm-hmm.
is it possible to somehow work in to your new idea for physics, the idea of like forced homosexuality? There's some sort of physical law to do with it, maybe.
Oh, God.
I don't know. I don't think so. Like I it's just what what I enjoy. It's my fantasy. It's just a fantasy. So it's not reality. It's just a fantasy. So I'm sorry about that.
Forced homosexuality is your fantasy?
Yeah.
How would that work? What even is that?
It's very similar to cuckoldry. So let's say there is a girl that I'm in love with, and she wants to bang another guy, and she wants the other guy also to bang me, just for fun, just for just for giggles.
Not cuckold.
You're a genius.
Do you think there's a difference between sticking your dick in a guy's bum and a girl's bum?
Big difference.
Why? It's still a bum.
Yeah, but one's gay.
They kind of look different to me.
Anyway,
Guys' bums and girls' bums.
does anybody
Maybe Mr.
want
Slave can explain.
My experience.
Does anybody want to talk about physics and stuff?
So that was physics.
I thought you were talking about black holes.
Let's get physical.
So, Mr. Slave, I do have a question of physics for you.
what's your favorite kidney, the left or the right?
No. Let's talk about physics. Let's say something. Let's.
That question sounded like a threat.
Oh, I just don't
Totally
want to
did.
sell.
So I
Just
actually
don't want
had
to sell his favorite organ online.
I actually had an interesting conversation today with Totoro and Omnivore. Omnivore is not listening, but
Are you sure they found it interesting, Mr. Slave?
Well, I'm sure they're. I found it interesting. That's all that is important.
What about the physics of the shape of the Earth? What do you think about that? That's some interesting physics.
No, there's nothing interesting about that. What's interesting about that?
What the physics? I don't know. Newtonian physics? What do you think about that?
I can easily derive a Schwarzschild radius from Newtonian physics.
What about quantum mechanics?
Quantum mechanics comes directly out of the ether assumption, the ether model.
Does it do that?
Yeah, because
Quantum mechanics too. So quantum mechanics gives you, ether gives you both quantum mechanics and general relativity.
and SR, it gives you SR, it gives you dark energy.
Is there an equation for that,
Well,
or
you can't get to GR without also getting SR. SR is a special case of GR.
Well, SR
So
SR comes out of the ether assumption.
Yeah,
Like
if GR
everything
would
else.
come out of ether, then SR would also come out of ether assumption because SR is just a special case of GR.
No. SR
But if your ether theory,
SR comes directly out of the ether model. SR is just
never mind.
SR. I mean, a dialect explain how you get time, for example, time dilation with a sound clock. So
I
the
watched the
ether.
video already. I told you.
wait, let's slow down, right? You obviously know, a lot of physics, right? Can you just tell me that how exactly you derive quantum mechanics from the ether? Give me some formula, some raw maths that I can look at.
I don't know why you want math. I don't disagree. I told you many times, I don't disagree with big physics. So my math is big physics math.
We're talking little physics right now. Little physics. How do you derive it conceptually, if not maths?
Conceptually. So once I realized from Newton that there is ether flowing through me very fast at 11 meters per second.
Yeah.
So I couldn't.
11 meters per second?
11
Let it happen.
11 kilometers per second. So the ether is flowing through us right now at 11 kilometers per second. So I couldn't figure out how can I have a particle? How could I be made out of particles that are surviving this collision with the ether? So I couldn't. So I went to sleep and I woke up and I couldn't figure it out. But then I realized, but what if there are no particles? Rather, everything is waving through the ether. And that explains particle wave duality. So everything is a wave, and everything is waving through the ether.
I don't know about this. I think you should stick to forced homosexuality. I don't think this is the topic area.
It was much more interesting.
Actually, Mr. Slave, could you do one favor for me? Could you say we need more cowbell, please?
Does anybody
Is it going to be okay at any time for us to actually talk about homosexuality? That'd be so refreshing.
It's a bit of a pain in the ass.
Do you know anything about celestial navigation, Mr. Slave?
No.
Are you interested in it?
Not really.
What shape do you think the Earth is?
It's a sphere.
It's a sphere. You just like to. Okay, so you're just doing alternative cosmology, right? I understand.
No, I don't have anything alternative. I keep telling you, I agree with big physics on everything.
Is the Earth in the center of the universe, or?
Or
That's
you
it.
don't agree with big physics.
That's
because
actually-
you say your ether.
That's
Your ether
actually-
gives GR and gives it quantum mechanics.
Well,
Right.
on
So
bacon,
they're
someone just
compatible.
asked a question, so let's get that one out of the way first.
Yeah. The question was very good. So the sun-centric model and the Earth-centric model, neither of them is more correct than the other. It's just that.
Which one do you think is true?
There's no true. The sun-centric model is simpler for understanding the solar system. The Earth-centric model is simpler for understanding the Earth-Moon system, or the
All right, which one do you agree with? Come on, chop chop.
No, I don't like your chop chop. So who asked another question?
Let me ask it a different way. Which one is inertial?
Which one is inertial? What do you mean?
Yes.
I don't know what you
Which
mean.
one is not accelerating?
What do you mean? I mean,
Yes. So you mentioned the Earth frame to deal with the Moon and Earth system, and there's the solar system frame to deal with the orbits of the planets around the sun. Right.
Wait.
Those are different reference frames.
okay, these are
They can't
different.
both be inertial.
I mean, when you see inertial, I know, like, I can speak Einstein, I can speak GR, or do you want me to speak ether? So which like in
English.
which? Well, but there's two different models. So in my ether model, I don't I have a preferred reference frame that is the ether. In Einstein, there is no preferred reference frame. So in which which language do you want me to speak? In Einstein or in ether?
And the one you think is true.
Well,
Like if I drop.
I believe there is. Look, I believe. I would say that the ether model is a simpler model of big physics. It's a unified theory. It unifies Maxwell with SR, with GR, with QFT, with dark energy, with black holes. Every phenomenon that I've ever with particle wave duality, with Heisenberg, everything, with Bohr, with de Broglie, with Einstein, with Planck, everything is unified under the ether in a very simple mechanical. It's a very mechanical universe. I don't have all the issues that you have, that people have, that big physics
you don't have
has.
the issues.
Excuse me?
You're not touching any equation. That's why you don't have any of the issues. Because you
course.
just talk about it. And then you
No.
don't get to any issue.
No. I just finished listening for an hour to the Dirac lecture.
Paul Dirac.
An hour of, like, I'm studying math full time. That's all I'm doing, math and physics. Like, I'm just studying math and physics full time. I don't
Right.
disagree with any equation.
Yeah, I know you keep saying it. But if you say that you have a unifying theory, right? So in quantum mechanics, there's a bunch of equations that describes the fundamental laws within that the model, right?
Like, for example,
and you have just a sec. And in GR, you get a different set of equations to explain the motions of the planets and all of that.
I don't know. I didn't finish my GR course. So that's the only one I didn't finish. I mean,
Well, you already know that you have a unifying physics that unifies even with GR. Because here's the thing, like those things that you're saying are unified by your theory. They have sets of equations to describe the behavior of the universe. In order for you to know that you're actually
I agree.
unifying them,
Yeah,
right?
yeah,
You have to find a way to unify all those equations. So
Yeah,
if you're saying you found a way to unify them, but you don't have a single equation to show, then of course you're not going to have any issue because you're not actually putting to the test anything you're saying. You're
Yes,
just
I
saying stuff.
agree. Yeah, I completely agree. I need to finish my GR. I need to fit together, the details. My right now is just intuitive. You're right. But everything I've done so far works very well. So far, so good. I haven't finished GR, but everything else, I haven't finished GR, but the little GR that I know works perfectly. The SR that I know works perfectly with Ether. It comes out of Ether. It just comes out of Ether. Ether gives you SR instantaneously. SR gives you a constant.
Show us.
As an ignoramus when it comes to this level of physics, what is Ether? Because I keep hearing people talk about it, especially from sort of, some of the more obscure parts of discussion that we have, but nobody seems to know what it is. How do you detect it? What is it?
So
why do you think it actually interacts with other matter?
Oh, I know this one. Hold on.
I think it smells like synonym. That's just
I
me.
will tell you, right. 1 second. The Force is what gives a Jedi his power. It's an energy field created by all living things. It surrounds us and penetrates us, and it binds the galaxy together. There you go. How about that?
Oh, we make it.
That's so, all day. This is the best description of Ether I've heard so far.
But what I want to get down to is the metachlorians.
So
don't worry about those.
If anybody wants to talk, I understand you people are having a good time. I don't want to take away your good
Is it
time.
okay for us to go back to homosexuality now?
Forced homosexuality.
No.
Forced, voluntary,
What
whatever,
I-
as long as it's homosexuality.
Let's balance you having a good time and me having a good time. So my good time is
Okay, let's balance it out. You go on mute
Alright.
for a little bit and listen to us discuss homosexuality.
Forced.
Oh, you're so mean.
Peter, are you
Mean is
from
my middle name.
Are
you from Scandinavia?
No, but close.
Okay, cool. That explains
Wait,
it.
what country are you from, Mr. Slave? You sound like you've got an accent.
I don't identify. I'd rather stay anonymous.
What continent? Can you tell me a continent?
I'd rather really not.
About what planet are you on?
Earth.
Okay, good. Right.
Doxed.
All right, give me another 20 minutes or so,
Located.
Mr. Slave, and I'll be able to tell you what continent, what country, and probably a fairly close system.
No,
Can you
please.
give me 3-star sites?
But Mr. Slave, by the way,
Yeah,
I
look
wouldn't tell
outside your
anybody
window
else.
for a second. Grab a protractor.
I wouldn't tell anybody else, Mr. Slave. I'm just good with
I'd rather,
accents. and I've traveled a lot.
I'd rather really not discuss me. I'd rather just discuss any topic. Specifically, I'd like to discuss physics, but definitely I don't want to discuss me.
But all we want to talk about
But
is
Mr.
you.
Slave, that's incoherent from what you said. You said you were happy to discuss any topic. That is the set of all. You would fall into the set of all. Therefore, does that not make you a topic?
Except for me. I don't enjoy talking about me.
I'm joking. That's about as close as I can get to a maths joke. So,
you know what?
I'm really vain. I like talking about me. Do you want to talk about me?
Do you have an independent variable for your ether proof, Mr. Slave?
What do you mean an independent variable?
Do you know what an independent variable is? Do you know what a dependent variable and independent variable? What's the other one called again? I keep forgetting. That's always the one I forget about.
Look,
control variable. Control variable. That's the one.
Look,
you
the
know what
only-
each of those
I
are.
would say
Mr.
the
Slave?
only thing that does exist in the universe is
Come on, you've been doing physics full time. Let's go.
the only thing that, as far as I'm concerned, existed is like not waving is the ether. The ether seems to be composed of actual particles.
Give me your experiment.
He said waving.
What's your hypothesis, Mr. Slave?
My hypothesis.
Do you know what's your observation? Let's start with that one. What's your observation?
I mean, everything leads to the ether. I mean, Maxwell.
No. We need an observation. We can't, have
You
ether
can't have ideas without
naturally
observation.
occurring phenomena. All right, Mr. Slave, start there. What do
Well,
you observe?
I'd like to contest the idea that it comes from living people. What if it comes from the dead people?
Could happen.
It's not allowed.
Right, what's your naturally occurring phenomena, Mr. Slave? Chop chop. Come on.
No, I don't like
I
it when
see
you
dead
say
people everywhere.
Okay, how about if I say it like this? Please, Mr. Slave, tell me what your naturally occurring phenomena is that you're observing.
No, come on, stop. Be nice. Don't
Just say it. Just say it. Just say it.
say
What are you observing?
So I was saying, I mean, basically, like if you look at Maxwell assumes the ether.
My hero.
If you look at
Slave Maxwell, yeah. Go on.
If you look at SR, assuming the constancy of the speed of light, that's just the assumption.
Wait. What's your naturally occurring phenomena that you're observing, right? Come on, Mr. Slave.
Tell him there's area between you and him. That's
So
what you're observing.
an apple falling. Why is the
okay, all right. Now, what's your hypothesis?
So the hypothesis is that there is a fluid that seems to flow into massive particles and drag everything in its path towards massive particles. And that is what seems to be gravity. That is a theory of gravity.
All right, okay. What's your independent and independent variable for your
I
experiment?
don't know. I mean, for which experiment? Like for gravity?
With your hypothesis, the fluid.
The fluid, I mean, it would be the Michelson-Morley, but to conduct it, like they didn't know about gravitational ether. So they thought about an ether wind. They were looking for a 30 kilometers a second horizontal ether. In my calculation, it's more like 300 meters per second. So it's 1,000, or is it? It's 100 times.
You suck the life out of the room.
Yeah, I mean, you asked him what were the dependent and independent variable.
I don't
He
know
said
what-
Michelson-Morley. Which one is the dependent variable? Which one is the independent variable?
But I don't know what those.
Is
What,
Michelson the dependent one? And Morley the
Yeah.
independent one? Okay, gotcha.
wait,
Do you know what an independent variable is?
no, I don't.
Do you know what a dependent variable is?
No. I mean, I
Do you know
know.
what a control variable is?
He said the magical word. He calculated. So let's see the calculation. Chop chop. Let's put it up. See.
I don't react to chomp chomp. So if you want to speak nicely, we
Well,
can.
just go ahead and present your math. How did you calculate it?
How about kowtow?
So the way to calculate it is to integrate MA equals GMM over R squared. The M's drop out, so you have A. You integrate A to V, and you basically you integrate from infinity until the radius of the Earth.
Right. Yeah.
So you start at velocity 0 at infinity, and you get 11 kilometers a second. You basically treat it's very similar to Schwarzschild. He just assumes the speed of light at the Schwarzschild radius, and I'm just assuming the Earth radius, and I'm looking for the speed.
Didn't you say 300 meters per second is your result?
No, 300
Okay, so
meters. That's the horizontal.
So what's the result?
It's about
Okay, 300 meters per second. So how did you arrive at that result?
the 300 meters per second horizontal at Ohio, basically in Ohio, because the Earth rotates.
In Ohio.
That's where they conducted the experiment. That's what they should have been looking for. And they would have needed about a 10 kilometer arm interferometer and not a 10 meter. They were using, I think.
Okay.
So of course they should have received a null result. Anyway, so
How did you hang on? Wait. Can you show the calculation how you arrive at that result?
yeah, so the ether is flowing into the Earth from all directions. So it impacts the surface at 11 kilometers a second. So you can imagine the ether it's like a waterfall. It's like it's raining or whatever. There's basically ether raining vertically on all of us right now, dragging us down. Obviously, it's more than just rain. It's a complete
It's like a ether golden shower. Gotcha.
Anyway, so at the north and the south pole, it's purely vertical. But at the equator, you would expect this rain to impact on.
Wait, Mr. Slave, right? Yeah, I mean, look, I want to get onto that experiment. So we were at what was your hypothesis again? If what, then what? What are you expecting?
What do you mean if what? I mean, I'm assuming. I'm not assuming. I mean, I'm assuming the apple falls. Once you assume an apple falls, I'm explaining it using the ether. So there is a fluid that flows into massive bodies. Basically, I'm assuming Newtonian gravity. So if you assume Newtonian gravity, so F equals ma and F equals gmm over r squared. So F equals F, so ma equals gmm over r squared. The little m's drop out. So a equals gm over r squared. So now you have a, and now you integrate and you get v. So you have an equation for v. I could tell you the equation. And you want...
Oh, you know what? You are absolutely killing me tonight. Just tell me what your hypothesis is. So if I say something like, if apple falls, then, I don't know, something else, right? Just give me an if-then statement.
Could I say something real quick?
Go on, Jesse.
Could we have a special VC just for Mr. Slade, and so the rest of us don't get bored out of our skulls?
I am losing my mind a little bit, to be honest.
Just to Mr. Slave and everybody else that is interested.
Exactly.
I'm afraid that's just going to be him.
Okay, I mean, if anybody should I go to live stream VC?
I don't think anyone's going to follow Mr. Slave.
You definitely should.
Okay, I'll go there. If somebody wants to come over, they're welcome.
Bye.
I'll count. Oh, Figoogie-goo. Oh, he's just joking. He doesn't want to talk. So they don't want to talk. Bro, unblock me. I need to thumbs up your comment. Anyway, it's fine. It's fine. It's like they don't have an argument. So, you know, that's actually very interesting. So they're but I don't want to, you know, I don't want to nag. I don't want to be a nag. Let's see what this live stream says.
Question in itself. When have you been free? Have your thoughts even been free? Because I'm going to tell you last night and the night before and today, and you'll tell yourself for the rest of your life, your thoughts are constantly going, and are they your own?
Well, Joe Rogan would say, as though they are you, because they're not you, your thoughts. You can be free from your thoughts basically by realizing that they're not you.
Exactly.
Well, you don't have to accept them. You choose as you.
There's about to be a lot of funerals.
Goddamn fire alarms going off.
I can give you guys a discount. Dude, is there like an issue going on at the building? Because I hear like a smoke detector going off.
Can you replace the battery?
What's going on?
No, I'm asking you. Like, I live close by. I'd be scared if the place is burning down. I hear a fire alarm.
Oh, no, somebody opened the back door. That's our back door alarm.
Oh, I'm so silly. I love kids.
Ask her if she can turn it off. It's triggering your anxiety.
I know my alarm. Yeah, so you don't really care the event. You guys will cater no matter what. You don't really like.
That's just it. And when the thermophobia came, it's just not swallow. They just can't swallow it. It's just hard to swallow piece.
And even when it comes to like AI inventions, China is leading on like they are leading by a like not even a running start. It's like 5 times lapping, because what China was, I don't remember the exact numbers, but I think it was something like 40,000 different technologies of AI, and they have thousands of different centers for AI, while America only has like 7,000. Korea behind with 4. I don't remember exactly the numbers, but when it comes to just general progression of technology and AI and how China is doing this, they're doing extraordinarily well, and they will continue to do well.
How do you know they will
Look, I
continue
mean,
to
like,
do well?
Say again?
How do you know they will continue to do well?
Well, there isn't any prediction of them falling down.
okay, the rest of his buddies are here now. Okay.
But
that's fine.
you don't know that.
Like if we look at the Chinese
The only
economy
thing- the
and we
only
look at
thing
the
that-
progress
the
of
only-
China, it doesn't seem to be going down anytime soon.
But
The
how
only
do you
thing
know?
I mean, like,
How do you know?
the only thing you can say we need to understand about the Chinese that they are a lot, right? I mean, they are 17% of the world's population, almost like 1/5 of the world population.
They've been progressing a
Long
lot.
history. Yeah, they have a lot of history, a lot of, I mean, a different culture to the rest of the world. I mean, understanding China is, I think, a bit complicated.
Yeah, but the
Just
Chinese,
anyone can come.
they used to be
But the
very.
average Westerner it is. And I'm saying this as somebody living in the West who's been studying about China for years.
Yeah, I mean, like, it's like it never ends, right? I mean, you think you understand them, but it's just they're very resilient, and that's why the empire stayed for a very long time, to be honest.
But they used to be
What
very
did,
poor.
Yeah, and they evolved and they have progressed faster than anyone has seen before. They have gone from having a lot of extreme poverty to reducing it by 80% in 6 years. So yeah, they're progressing very fucking well, better than any capitalist nation in the last near future.
How do you explain it?
Bigger, better, faster, stronger.
Sorry, in the near past. That's the word I meant to say.
And what's your explanation?
What?
Whoever is talking is very quiet.
What's I'm quiet?
Yeah, I
Yes,
have to have you
you're
at
extremely
200%. To, yeah.
Really? Let me check. Oh, thank you for letting me know. 1 second. So I'll fix it. But what's your explanation for why China is doing so well?
How China is doing so well is because it has extraordinarily good economic policy that has allowed that has allowed China not to be robbed by other nations.
They're pretty
Um,
authoritarian as well, so they like control their people, right? I don't know.
No,
Maybe
that's not currently the subject at hand. Thank you very much.
Well, I mean, that would
But-
still
but
have
no,
something to
hey,
do. That would
hey,
still have
hey,
something to
we're
do.
talking about how the progress has come about, not about how you
Exactly.
think how it's authoritarian. Thank
and that
you.
would
And
still-
if you
it
wouldn't
would-
interrupt
it would
me,
still have
right?
something to do
Thank
with
you.
it.
Thank you.
That has.
Thank you. Thank you.
I think they're.
So-
I mean, the Americans are drawing a parallel with their own country. I mean, America is a clearly authoritarian country. It's not just by a single
Because you
person,
only-
but
because you
by,
only
by
have
the
one
Federal
choice.
Reserve and a bunch of agreed upon. I mean, corporates.
So-
maybe a few people.
You can get progress
So
that way.
when it
And then
comes
you can
to
they don't
China,
gotta whine about it.
so
No one
China,
did
when it
anything
comes,
wrong.
Jimmy, please, when it comes
You
to
fucking
China,
freak me out, dude.
thank you. If you're going to keep interrupting, you're not going to be talking at all.
I've been out in Sub-Zero and been absolutely warm. You know, because again, it's about positioning the fire, where you set up, type of fire you build, etc. I think my epiphany was learning how to build a Swedish stove.
Can I
Just-
can I interrupt again? I'm sorry.
Sure, no worries.
So I presented an ether theory, and so far no one has been able to disprove it, right?
Well, I think you've
That's because
presented
it's true.
I'm
That's
sorry.
like saying I have a theory of unicorns causing gravity. They're just so small you can't see them. Can you disprove that?
Yeah.
I mean, the whole point of that's the whole thing with pseudoscience. science by its nature must be falsifiable. If it becomes unfalsifiable, then by definition, it is not science.
You know, that's a good question, Sea-Line. Mr. Slave, how do you falsify your theory?
There's at least 2 experiments that I.
Go on, give me 2.
Well, I tried explaining to you just one of them.
Quick, come on, stop this meta right now. How do you falsify? At least give me one. Just give me one falsifier.
So, Michelson and Morley, if they would have run their experiment.
Oh my god. Oh, you're taking me on a fucking. You know what? I'm done.
All right, I can tell it very quickly. He's going to say if they did the Michelson-Morley experiment, they extended the interferometer out to a 10-kilometer range, and that found evidence that could disprove his theory. Correct?
Okay.
So that's correct, but I can A, prove it mathematically, and B, I have a setup that doesn't need a 10-kilometer. I've been able to reduce it. I can fit the experiment inside a small room. If you want, I'll explain to you. That's one experiment.
I don't think we need to explain.
I could send you a can of ether if you need it that bad.
Don't fall into a jar, Jesse, and send it to him. That's not nice.
It fits in a suitcase.
I mean, you people.
The thing I found telling, Mr. Slave, when I asked you what is ether, what how do we detect it, what's it comprised of? Even at a theoretical level, you had nothing to give me.
I mean, look, if you want to have a normal conversation, why don't we go to a separate VC and have a normal conversation where I'd be able to complete sentences? Because in here, it's really not productive. It's not productive.
Look, just be a bit more interesting, Mr. Slave, when you speak. I mean, it's like miserable to listen to.
Also, do realize, I mean, again, forgive me if I'm wrong, but I don't think English is your first language. So it can take a little bit of time to work out what you want to say, phrase it, put it in a form, and then spit it out.
Anyway,
give them a little bit of latitude.
Anyway, if anyone is curious to disprove my ether, I'm welcoming. I'm here to stress test my ether theory. I'm presenting it. I'm writing papers. I'm looking for feedback. You want to give me feedback? That's fantastic.
But I think
can
what
I
I
say
would do.
one thing?
John.
Okay, I didn't notice Mr. Levy was not a native English speaker, so I mean, I'm not sure if my opinion counts because I'm also not one, but I think his English is pretty good.
Anyway,
it is very good.
Anyway, my point is that I'm here. I'm not like I don't consider myself similar like to a flat earther. I never had my own theory about the universe. But 2 months ago, I was just thinking about black holes, and as I've been thinking about them for many years. And I sat down and I did, the integration of A equals GM over R squared, and I got the V, and it just came out of the equation. I mean, everybody agrees.
Yeah, right, Mrs. Slave. When you think about black holes, what do you think of?
I think that there is ether. At this time, I'm thinking about the ether.
What do you imagine in your head when you think of a black hole?
That the ether is flowing at the speed of light.
You imagine ether. Now, what does ether look like?
It's what you call the vacuum.
How do you imagine a vacuum?
I imagine the ether. I don't imagine the vacuum.
What are you imagining when you imagine the ether? Like, what do you like? Does it have a color? Does it look like anything?
It's a fluid. It's just a fluid.
Fluid.
Mhm.
And you can see the fluid.
No, we can't
No,
see.
you can't. So, what are you picturing in your head?
A fluid, like water.
You picture water, like as in physical water you can see.
Right, but you can't see this water.
So you can't see it. I can't picture gravity in my head. I can picture its effect, right? I can't picture gravity. You understand?
I can picture the ether because I can picture.
What are you picturing in your head? Describe it to me. What color is it? What does it look like?
It's no, it's
What
a
does it smell
fluid.
like?
It's like water. I imagine a fluid that flows from high pressure to low pressure.
All right, solid. Thanks for that. You're imagining water. All right, solid. No further questions. No need to follow up.
Well, again, not wanting to be mean, but if you're imagining it to be like water, to put something under pressure, obviously, you need an external force to the medium that's being put under pressure.
Right.
So surely that takes you back another step in your problem of what's causing that pressure to cause the motion of your inverted finger quotes ether wind.
Or
don't have-
your understanding water could be wrong. Water could just be liquid air.
I don't have
See the problem?
I don't have ether wind. So I do have dark energy, and dark energy is, that's the.
I just use that as a colloquialism for the flow of the ether which you were describing.
Okay. Yeah, but I just don't like the ether wind. That's where everybody got it wrong. So for me,
Ether flow.
right. So the ether flow. So the ether, as it flows into massive objects, the universe would have run out of it. The universe would have collapsed. So that's why Einstein added the lambda, the positive pressure. So the dark energy is exactly the creation of new ether that creates positive pressure, that creates the expansion of the universe. And now we have positive pressure, and the ether, when it interacts with massive particles, it actually imparts mass through the Higgs mechanism to these particles, but then it also gets annihilated. So you get a vacuum, you get low pressure, and then you get a pressure gradient from everywhere where there is positive pressure to any massive particle where there is low pressure, and then you get a flow. So the reason why the ether is flowing through us right now is because of a pressure gradient, which is just gravity, which is just a Gaussian flow, which is, it's just Newtonian gravity. But it's just my gravity is mechanical. My dark energy is mechanical. And now this dark energy, now we understand, it has nothing to do with the vacuum and zero energy state. It's the creation, it's the positive pressure. It's not, the fact is that the ether vibrates, but that's why the prediction of dark energy is wrong. So I can explain to you why they're getting the dark energy prediction wrong. They're confusing the creation of ether with the fact that when ether gets created, it naturally vibrates.
Does the ether have energy associated with it?
Yeah, this is just a vacuum. Everything I'm saying, just replace the word ether with the word vacuum. I'm not saying anything different, just that my ether...
Well, vacuum doesn't flow, so that doesn't work.
Of course the vacuum flows, because otherwise
No,
why...
it doesn't.
Yes, it does, because why is a black hole black?
What else color would it be?
Oh.
Do we know that a black hole is black?
Yes, we've seen pictures.
No,
no.
we've seen images that have been produced that aren't color variant. In fact, the colors were introduced in there to show differentials.
Well, and I think pictures of black holes are just pictures that just isn't showing something.
So
Yeah, I
vacuum,
mean,
but
so
we
in
look-
your theory, vacuum can flow.
We look at the sky and we see that at the center of the galaxy, the stars are moving fast, but it's around a
Oh
star
my
that
god,
is...
it's Mr. Slave. Hello, Mr. Slave.
Hi. At the center, there is a supermassive star at the center that is black. So it looks like black holes are black. There is no star at Sagittarius A star. There is no light coming out of Sagittarius. It's like a black spot at the center of
Hey,
where...
Gamma. We managed to finally get something out of him. Apparently, ether is vacuum, and ether flows. So I guess vacuum flows.
Nice.
And it flows into objects.
I'll be in the other VC eating roots and stuff, wild roots and stuff.
What? Eating wild roots.
Is anyone finding my thesis at least interesting?
The title is the most grabbing part of the document.
The improved one?
Yeah. Wait, did he make another one?
No, I removed.
No, he's just monologuing.
What do you mean?
I think the problem is it's the type of thing, Mr. Slave, where rather than have it as a discussion, you want to provide a document that a group of people could read and then come back at you with questions about your assumptions and abstractions that you would necessarily have to use in a mathematical model that you're putting forward to support the theoretical aspect of your approach to the topic. It's about the nicest way I can put it.
Yeah, I mean, I'd love to write. I mean, that's why I submitted the papers so that we can, you can give me some feedback. But instead, you decided to just have fun and give me zero feedback. But sure, I'd love to write. I mean, I was invited to this server by Sea Lion, and he wants to collaborate and write this paper. So.
I thought you already had a paper.
I mean, it's preliminary.
But you said you submitted it
to you guys.
Bear in mind, you're in a group here of people who aren't idiots that will actually listen to what you say, and I suspect from what I've gathered so far, will fucking remember it.
Yeah. I mean, the question is if you're ready to accept our suggestions that we made to your paper yesterday and work off of them to make something better.
I mean, I'm in the process of removing all the comments because it's nothing but, it's complete garbage. I can't even scroll through the document because of all the nonsense.
The Mein Kampf, the 1,400 pages of Mein Kampf are taking it down.
Yeah, I mean, you guys are like completely wasting my time. Like my time is very valuable, and I don't want to.
Extremely.
I don't want to waste my time.
Well, I think we all fit in that same category, don't we? Everybody's time's valuable.
Anyway, I was invited to this server, to have a productive time, not to waste my time. So it's okay to laugh a little bit, but we can't only laugh. We need to balance laughing with some productive work. So
That's a you thing. That's for you. That's for you to go back and present a document that we can all interpret and enjoy. See, obviously, you're just playing the victim here, when in fact, it sounds to me like you've just submitted a badly written document. So, I mean, change it. It's up to you to change it, not to us to fix it for you. You have to fix it. That's a you problem. Thank you.
Right. So right now I am spending a lot of time just cleaning up all the garbage comments that you guys made. I don't even know how to do that. So
Well, you should have made an original.
No,
you should have made it an original copy.
I did not expect. I didn't expect. So much spam. So much spam response. Anyway, look. What I'm saying is, from now on, let's be a little bit more productive. That's all I'm saying.
Yeah, and get an original copy and don't let anyone else be able to change it.
No, it's just comments, but you guys are overloading the comment section.
Again, you guys. Why are you blaming other people? It's a you thing. It's not us guys.
No, it's actually not. We kind of did fuck it up like crazy. Have you seen the document? Have you seen the document?
No, I'm just hearing this rhetoric cycle
look
around.
please,
You guys.
Hold on. Let me get you a picture of the document.
What, the original or the one that's the latest version?
The improved version.
The improved version. Hold on.
I wish I
It's
could
pretty
just.
bad.
I wish I could just remove all the comments. Wait, you know what? Maybe I can go to the history and just go back to the old version.
Yeah, you can. No, go back. No, Control Z.
Me?
Yeah.
What do you mean Control Z?
Can you leave that version alone, make a copy of it just for posterity?
No.
Yes. That's history. That's server history. You can't do that.
I didn't actually get to look at it at all.
But here's a little tidbit. This isn't the
What do you want, the original or do you want the improved versions?
The one we call improved.
Oh, okay.
Here's a piece of this is the old one. This isn't the best version.
What you guys did is so bad that my my tab is crashing. I can't even open.
Well, that's what happens when you have 1,400 pages of Minecraft. Google Doc, I guess.
Okay, I'm gonna remove.
Did we really not get a screenshot of the document at its peak? Did we miss history, Totoro? That's gone forever now.
Maybe, yeah.
Oh.
This is a valuable lesson that everyone should listen to. Never put a Google Docs for everyone else to look at and edit.
No, it's not edit. It's just comment.
Here's another version. So this was preserved.
Let's see.
Are we talking about the same document, the one that was done in Comic Sans?
Yeah.
Yes.
I thought so.
It was improved over.
So what do you mean by comments? I thought the comments is actually the re-editing of the document.
It is, but they're not like taken completely into. They're not immediately adopted into the document. You can just delete all the comments. They're just revisions, basically.
There's a way to remove all the comments?
Yeah.
How?
You have to go into Files, search up System32, and your executive folder.
It's
Or, hold on.
It's a Google
Yeah.
Docs.
All right, no, I'm not that mean because I know Mr. Slave would actually do it. Never mind. Would that be too far, Totoro, if I actually did that?
If we left and never came back, we would know why.
That you don't think that would have been too mean?
Do you people do anything besides being mean? Are you like, what is this the only purpose for you to have this, to be on this server? Just to be mean, just to bully and harass?
Oh, once you get to know us, you'll understand.
I mean, at one point or another, don't you find your life to be just a little bit boring, just being pure bullies?
Well, not when you're in my life. Mr. Slave, you make it complete.
Here, I've added the macOS instructions.
Yeah. Why is Mr. Slave on Mac?
Oh, just in case.
Yeah.
Oh, I want to be inclusive of everybody.
Yeah, if you for some reason have a Mac, at least you can do something other than.
So there's
stop bullying.
So there's no way.
Sorry.
There's no way we're ever gonna have a normal conversation about physics, is there?
Yeah, that's possible.
How? What do I need to do to have?
We'll bring up the topic and we'll discuss that topic.
I mean, we can discuss anything in physics. I mean, I'm really curious about quantum mechanics or GR or SR or ether or particle wave duality.
I don't know how many nerds are here that are able to cover all those topics.
No one actually. No one knows about that shit. That's magic.
But there you go. That's That's the response that I'm
Because
getting.
Yeah. Okay. Even my ego is not large enough to say that I can understand any of that, right? So like, I have a pretty large ego. I'll admit that, and I can't even admit that I understand that stuff.
What don't you understand?
It's a very complicated subject.
SR is complicated?
Well, with mathematical derivations of the whole thing. I wouldn't say okay. I don't understand something until I can derive the equations for it.
Wait, time dilation is difficult to derive?
No, not necessarily. But if you're talking about deriving the entirety of SR and GR, that's when I'd say I would understand it. But
All right, but time dilation is simple, right?
yeah,
Okay, I mean, so okay, but
if you're just talking about calculating like Lorentz factor and everything, sure, that's pretty easy.
okay, but
I'm sure you know
SR.
how to do that, right, Slave?
What?
You know how to calculate Lorentz factor?
I mean, I don't remember if I've ever done it, but I've watched YouTube videos that derive it, and I follow step by step, and I confirm that I can understand each step. I don't know if I would remember how to do it right now.
I think that's a no.
It's fun. I don't know how to do it off the top of my head either, but I've done it before.
But
I'm sure Totoro could do it, right, Totoro? Yes, I could do it off the top of my head.
I'd probably fumble about for a minute or two, but it could probably do it.
yeah, I
Fine.
mean, yeah, I mean, but SR depends on the assumption that the speed of light is a constant for all observers, for all emitters and receivers, whether they're moving, stationary. Does that make sense to you?
Yeah.
Yep.
Yeah.
That the speed of light is a constant?
Does
Yes.
that bother you? Do you think it shouldn't be a constant? Is that what you're trying to ask?
I mean, why is the speed of light a constant?
I mean, the way I think of it is just that since photons have no mass, they have no propensity to remain at rest at all. So they just go the speed of light because that's, for some bizarre reason, defined as the speed limit of the universe. I don't know why. I couldn't tell you why the speed of light is the speed of light. It's just the
No,
way I think
that's
about it.
not the question. The question is, why is the speed of light a constant for in all reference frames?
Because if it wasn't, everything would break down. I mean, it's the speed of information.
No, that's not the question. Why is it a constant?
I told you what. It doesn't necessarily have to be a constant. I'm sure you could have a universe where it's not a constant. Just wouldn't make any sense.
What do you mean it wouldn't make any sense?
Because information would have varying times of travel depending on your reference frame.
So what? So what? That's
like time travel and stuff, which wouldn't really make sense.
Yeah, you could get causality paradoxes that way.
Yeah, but it just so happened that the universe apparently likes to make sense. I don't know why. I'm not God. Appears to be that way.
Okay, but do you have a mechanical explanation why the speed of light is a constant? You're working backwards. You're saying in order for the universe to make sense, whatever that means, I need the speed.
Time to be linear and not.
Yeah, that's
and
still.
violate and be
Yeah,
causal.
Causes to precede effects. Yes.
Yeah, that's still working backwards. So in order.
Well, once you find a cause following an effect, then we can talk. Until then, I'm going to go with all the explanations that we've seen or all the cases that we've ever seen it. Anybody's ever been demonstrated, causes always precede effects.
It just appears that the universe wants to make sense, Mr. Slave. That's my answer. I don't know why.
But you see how that's a magical universe.
Absolutely, it's weird. Okay.
That's my point. It's not mechanical. So this is where that's not science.
I never said it was science. What about science is the speed of light being constant? There's no.
No,
That's
so
just a
for
statement.
so but if you assume ether, then the speed of light is a mechanical. Then you have a mechanical explanation why the speed of light must be a constant.
Okay, so ether brings reason into the universe, is what you're saying.
No, ether creates a constant speed of light.
How?
That's one of the papers that you made fun of. You didn't read it. Here, I'll try to bring it up.
I can't read it unless you give me complete permissions to write everything again. It would just be impossible for me to read it without having edit perms, you know? It's just how it is.
Wait. It looks like the paper is completely gone. Like all the images are gone. Everything is gone.
Might have went too far back, maybe.
Let's see. Okay, this paper was not destroyed, but the first paper was destroyed, apparently.
Ah.
Oh my god, it's completely destroyed. It's completely gone.
Please don't cry, Mr. Slave. That'll make me feel really bad.
Hey, Pazza, what are you doing over here?
C-Line, I have some really bad news.
What?
I think we may have completely fucked Mr. Slave's paper.
Oh, really? You can't revert it?
Yeah.
No.
I'm sorry for being a bully to Mr. Slave. If it turns out it's completely irreversible.
Yeah, it's gone. It's completely gone. All the diagrams are gone.
I think we've learned a valuable lesson here.
Is that I'm evil? I feel horrible. Was it worth it in the end, C-Line? Did we do something? Are we the enemy?
Are we the baddies?
Are we the baddies,
Well,
C-Line?
I'm sorry, but if you don't follow the rule of three, you know, you got your primary, your backup, and then your offsite backup or off system backup, then, you know.
But who could have foreseen this would happen on a Google Doc that people could edit?
No, people could not edit.
So wait, what happened then? How can you not just remove the comments?
Mr. Slave, did you do something bad? Did you end up deleting it by trying to remove the comments?
That seems like what would have happened.
Oh, Mr. Slave.
Oh, it seems to be fine. I opened the wrong. Apparently, it was placed. I mixed two versions.
We would have been set back like 300 years in physics if that document was deleted.
No, it's a couple of hours of work. It's just like 2-3 hours of work.
Bad, Tora.
What? I didn't do most of it.
No.
You should have been here when it was getting done first, Russ. It was funny then.
Should have been moderating. You're supposed to be the adult, Totoro. I'm only a kid. You can't do this to me.
A 19-year-old kid?
Yeah.
You're basically a toddler.
Yeah. You were my supervisor. You let me do this. I take no responsibility for my actions.
Yeah, I don't know much Mac, but I do know a bit of Linux. Bad Totoro.
Evil man.
I had no part in this. I play no part. I'm complete innocent bystander.
Terry, your mere presence makes you guilty. Boomer told me.
Boomer?
I didn't say anything. Well, look, guys, I think what we all do, if there's 20 of us and we all contribute 6 minutes each, that'll give the 2 hours back that Mr. Slave would like, and we'll all be happy and we can all be friends.
No,
and
no,
hold
no.
hands.
Everything is fine. I found the document.
No, I want to help you. We must help you. We must fix and right our wrongs.
Sure. Am I getting compensated for this?
Well, it's only 6 minutes you've got to contribute. Can you afford 6 minutes?
You're gonna have to pay me.
1 second, 6 minutes.
Yeah.
Don't want to be mean, but someone will have to pay me about £50 for that.
We'll start a GoFundMe.
6 minutes. Damn.
Fuck, man, you charge like a lawyer.
Yeah, he's trying. That's
Lawyer wasn't exactly where my mind went, but okay.
Yeah.
Okay, yeah.
Yeah.
What
There's
can I
better
say?
ways of spending your money.
There's a sucker
Better ways of
board every
spending your
minute.
Every time I'm trying to revert to a previous version, it crashes. The tab crashes.
Probably because of that's probably because they're trying to recursively delete 1,400 pages of Mein Kampf.
Yeah.
Who would have Mein Kampf on their fucking computer?
I don't know.
Research.
So the guilty party better not incriminate themselves.
I was going to say, if it's anything to do with this document, you can then say that 6 minutes is going to cost you about 150 quid.
Yeah, you're gonna have to type the entirety of Mein Kampf for him.
My morals are very, very much.
Mr. Slave, you can go to the tools and you can reject all comments. You don't have to reject them one at a time.
I'm just trying to revert to an earlier version, and it's crashing.
Okay, well, if you go to, because everything should have been added as suggestions, you can choose reject all. And that should get rid of everything.
In
Want to
tools,
share your screen, Mr. Slave, and we can help you out live?
there's no tools reject. If I share, then no one will hear you on the YouTube stream. I want everyone to hear you. If I share this screen, they're not gonna hear you, and they're not gonna hear you. So,
Wait, go to tools.
Yeah, I'm
and then the
tools.
third one down is review suggested edits.
Okay. No suggested edits.
There's no
Review.
Review suggested edits, and it says no suggested edits.
Correct.
Did you accept the edits?
No, I rejected. I clicked on each and every one's X, but some of them don't have X's.
Okay.
Oh, I guess these are just actual comments. I see. Okay. So all the changes have been, so that's fine. Okay.
Who kept contradicting me about edit when I said the word edit? You just mentioned it.
What?
It's Ed. His last name's It. Ed It. It's a person. It's not an
No.
edit. Keep up, will you, Terry?
I'll try to. You know, I'm old boomer.
I know,
Anyway,
so am I.
does anybody want to talk about something like
Yeah, we can talk about something.
like
We can
the
talk
wave?
about something.
You want to talk about the wave equation, or
Well, let's talk about that fourth stuff that you were fantasizing about. That seemed very entertaining.
Yeah. Forced homosexuality. Let's talk about that.
Yeah.
What?
Well, something. So if two people are having sex and they fall into a black hole, what happens?
Anyway, so does anybody want to talk about physics?
Well, we just were. I just
We are.
proposed.
We're on black holes.
I have a question for physics. I have a physics question.
All right. Omnivore's
Okay.
tuna. Go ahead, Omni.
So this is one that I kind of know an answer, but I'm not. I have no confidence it's necessarily the right answer. So in general relativity, we have both coordinate and proper acceleration, right? The difference being that when something is in free fall, it's undergoing coordinate acceleration, meaning that you can you can change the acceleration based on your reference frame. You can change what object is accelerating based on your reference frame. Now, my question is this: why is it's two parts? Number one, why is it an acceleration? Why not just a standard velocity? And the second question is, where does the energy come from for the acceleration?
Yes, and Walmart are the two answers you're looking for.
Say again?
Omnivore's
That's
not
all right.
taking the question, so it's hers about to die since Omnivore can't physics at all. It's over.
What was that?
I'm saying since you can't physics at all, the conversation's gonna die.
Wait, Omnivore, what's
Somebody-
your question?
That was my. I just said it.
Yeah, let's go over it.
Can we define what energy is in the context of the question?
Ability to do work.
Mm.
I'm using the standard physics definition.
So wait, could you repeat the question?
When an object is in free fall,
Right.
according to general relativity,
Hmm.
it is at rest. However,
Mm-hmm.
but from the perspective of somebody on the ground, watching whatever it is that's fall,
Mm-hmm.
it is certainly appears to be accelerating.
Mm-hmm.
And as far as we can tell, that is what we call coordinate acceleration. So the first part of the question is why acceleration and not, say, a standard velocity? And the second question.
Wait, let's
is
go. Let's one question at a time. So
Okay.
So I'm looking at an apple accelerating.
Mm-hmm.
Yeah.
Yep.
And from the.
So are you familiar with the difference between coordinate acceleration and proper acceleration?
Not really.
Okay. So in general relativity,
Mm-hmm.
coordinate acceleration, in general relativity, proper acceleration, defined as what an accelerometer measures,
Mm-hmm.
you cannot changing your reference frame will not make an object undergoing proper acceleration appear to not accelerate. It will always appear to accelerate from any reference frame because it is undergoing proper acceleration.
Mhm.
However, when an object is in free fall,
Mm-hmm.
it is at rest and can be said to be undergoing coordinate acceleration.
Mm-hmm.
Okay, coordinate
it.
acceleration is a let's see, how would you describe it, guys?
No, it's fine.
Coordinate
I
acceleration-
understand. So the apple is undergoing coordinate acceleration, but not proper acceleration. But if I'm pushing a car and it's accelerating, that's proper acceleration because everybody
That's proper
agrees.
acceleration.
Because everybody agrees there is a force, and F equals ma, and there's an imbalance of forces, so it's accelerating, so it's proper.
Kind of, yeah. I mean,
Okay.
more or less.
All
Okay,
right.
so then my question is twofold.
Mm-hmm.
Number one, where is the energy coming from for this acceleration?
Which
and
one?
also, why
Wait, which
does
one?
an object that general relativity says is at rest
Wait,
exhibit something that appears to be acceleration?
Wait, why are you asking two questions? Why not just ask one and let's try to figure one out?
Well, yes.
So what?
Because maybe somebody will think, "Oh, that's too easy."
Okay. Wait, so let me try and understand the first one. So you're asking where is the energy for the coordinate acceleration coming from?
Yes. When an object is in free fall, according to general relativity, it is at rest.
Okay.
So
I think we need Gregory in on this one. Gregory would help us solve this puzzle. Can you DM Gregory and get him to come in for this one?
I'll tag him
See
real
live?
quick. Yeah, I'll
Yeah,
try
if you
to-
could.
Right.
Gregory's our man. This will be great.
Wait, so from the reference frame, from my reference frame, gravity is doing work, right? The coordinate, right? The coordinate acceleration, you could say it's converting potential energy into kinetic energy. There's no work. It's just there is no, just a conversion of energy from potential to kinetic. That's
Right.
from my perspective, my frame of reference as standing on the ground.
Yeah.
Okay.
But according to general relativity,
Mm-hmm.
the object that is free falling is at rest.
Mm-hmm.
So so if it's said to be at rest with respect to GR,
Mm-hmm.
why does it appear to accelerate from our perspective?
Mm-hmm. So Einstein would say that the apple is following, I think, a geodesic.
Correct. Yes.
Which is the shortest path, basically, or the least, the path of least action. It's following the path of least action,
Okay.
which is geodesic in GR. Okay, so
Oh Jesus! I think Mr. Slave knows more about the GR than me. This is kind of scary.
Well, he's right. He's right. I mean, he's right about that. But the
so
question is, why does it appear to
Mhm.
accelerate?
I mean, that's the old question. Why does the apple fall? That's why I came up with the ether theory. But
So
Mhm.
I'm not asking why it moves at all.
Mhm.
Okay, because I would hold that it moves because of curved space time.
that doesn't mean
And that-
anything. But fine. Mhm.
Well, it does to me. All right, an object. The way that you
Mhm.
change the first law of motion. The first law of motion, as learned by everybody, is an
Mhm.
object at rest will continue to remain at rest
Mhm.
until acted upon by an outside force,
Mhm.
right?
Mhm.
Something like that.
Mhm.
However, if you want to tune that for general relativity, it is an object at rest will continue to move in its geodesic
Mhm.
until acted upon by an outside force.
Mhm.
So the object is therefore assumed to be moving in its geodesic.
Mm-hmm.
That's a perfectly, as far as I know, that is a perfectly fine conclusion to come to from a relativistic standpoint.
Mm-hmm.
You could say, that's not a problem.
Mm-hmm.
However, what you can't do is then what that doesn't explain to me is then why you would have any why would that appear to be acceleration as opposed to
Right, but so Einstein,
a single velocity.
right? So Einstein would say that we're accelerating, right? We're experiencing a force, so we're accelerating. I'm accelerating towards the apple. I'm accelerating. The floor is pushing me up. F equals ma. I'm being accelerated upwards. And relative to me, it appears like the apple is falling, but I know there's no force acting on the apple, so the apple is stationary. I feel a force, therefore I'm accelerating. And then you
maybe. I mean, yeah, something that would close to that. Yes.
I mean, I don't know that, right? I according to Einstein's equivalence principle, so I might be in a space station. I don't know that I'm on Earth.
Right. Okay, yeah, if we're gonna look at it that way. But yes, I could say that I feel like I'm moving, and therefore the apple is at rest. Of course, in anything approximating our everyday experience,
right,
we're going to perceive the apple as falling. But yes.
Right. So what's the question?
So the question is the question is twofold. Number one,
Mm-hmm.
where does the energy come from for this?
The energy for me to be
The energy to move the object. Why in order for the object to move?
But it's not.
In order for the apple to move at all.
It's not. It's stationary.
Well, okay, so then the ground is moving towards it.
I mean, the whole time when the apple was attached to the tree, it was being accelerated. There was a force acting on it. And then the apple got detached and stopped being accelerated. Finally, it's free. Now it stopped Now it stopped accelerating upwards because we're in a spaceship. So the whole time we were in a spaceship, we have a tree in the spaceship and an apple on the tree. And at one point, the apple is ripe and it got detached. Until then, it was getting accelerated with the whole spaceship because of the engines they were on. They're still on. So it's the engines are doing work. The engines.
Well, if assuming we're not on a spaceship, if we're on Earth, does that mean that the Earth is doing work? All right, my let's talk about science thing didn't
What?
There doesn't seem to be a lot of uptake on this.
No, this is a great conversation. Finally, we're having a normal conversation. This is revolutionary for this server.
Okay.
This is unbelievable. Okay.
I hold that the energy has to come from somewhere.
This is the first conversation I'm having in my entire life about GR. I've never spoken to anyone about GR.
Okay.
So you're asking a good question. Because you're saying, okay, in a spaceship, the spaceship is doing work. It's accelerating me over distance. It's pushing me over distance.
Right.
Um,
Well, I'm thinking specifically about an apple falling from a tree on a planet, because we don't.
yeah.
We generally do not, although we can say that from the perspective of the apple, it appears that the planet is rushing towards it, and that's perfectly fine because it's coordinate acceleration. We don't. We in our conception of the dynamic forces involved, we do not think of the planet as actually moving towards the apple. That is just, a point of perspective. So I will tell you
that's what I was going to ask. You're saying the apple would just float there, but the planet is traveling towards the apple? I don't get it.
So according to general relativity,
the apple accelerates towards Earth's surface, and Earth's surface accelerates towards the apple, but not
No.
nearly as much as the apple accelerates.
No. Yeah, I mean, okay. So first off, yes, there is, according to Newton, there is a mutual attractive force between Earth and the apple. That is correct. However, the distinction between coordinate and proper acceleration, and once again, I'm not a physicist, so don't. Nobody should be quoting me on this, but secondly, I'm pretty sure this is correct. The apple falling is not proper acceleration. If you let an accelerometer fall, it will show no acceleration. It will show as being at rest. So, as the apple falls, you can, according to relativity, you can do the math both ways. Or do the reference frame both ways. You can have from one reference frame, from the apple's reference frame, it can be standing completely still. From the Earth's reference frame, the Earth is still and the apple is falling. Both of them work. Both of them are, according to GR, equally valid. Okay? Now, from our perspective as human beings, we are definitely not inclined to see the apple as moving, the Earth as moving, because that's not how.
Can I get a little clarification?
Sure, by all means, yes.
Yeah, I just had a question because, when it comes to gravity, I always hear you guys bring up acceleration, which is, the rate at which the speed is changing. But how come speed is never brought up? Because speed would just be how fast it's moving. So, I mean, if you use acceleration, sure, it's not moving. But if I told you it's speed, then it is moving, right?
So, kind of, but not. So first off, yeah, I understand. I think I see what you're asking about, but let me try to be totally clear about this. The general relativity statement that the Earth can be flying towards the apple the same way that the apple is flying towards the Earth. The idea that both of those are
valid,
equivalent, in no way means that we should think of the Earth as flying out of its orbit to go chasing falling apples or anything like that. That's not what it implies. What it implies is that from the perspective of the apple, in free fall, let's assume it's in a vacuum so that there's no air resistance or anything else going on. It's just in free fall, from our perspective on Earth, hurtling towards the ground. The apple, if it goes to measure its acceleration, says, hey, my acceleration is 0. I've got an accelerometer, and the accelerometer shows no acceleration. I am at rest. And the person on the ground who's standing still and not moving anywhere says, hey, I've got an accelerometer too, and my accelerometer shows no acceleration. I am at rest. That means neither object is undergoing proper acceleration. However, from the perspective of us on the ground, the apple is for sure accelerating, and if you're standing under it, you will get bombed. Same way when the apple hits the ground, if it falls from enough height, you're going to get applesauce. So the idea that there's speed, yeah, the speed is you can figure out the velocity, but velocity, just standard speed, is always referent to something else. You can't just have speed. You can't say I'm moving at 10 meters per second. It has to be 10 meters per second relative to something else, because if you just say I'm only moving at 10 meters per second, well, if you're on Earth, the Earth is hurtling through space, the Milky Way galaxy is turning, the galaxy itself is moving, the sun is moving in the spiral arm, etc., etc. So there's a whole lot of motion. In order for you to say I'm moving at 10 miles a minute or whatever, you have to. Oh no, Jerry is Jerry is upset. Jerry, you shouldn't be listening to this. You're going to hurt
This is
yourself.
for reasonable people only. You're not allowed to be here.
It's just, I mean, this is not your thing, Jerry. This
Comedy
man's
is
got to
my
know his
thing.
limitations.
Comedy is my thing. Okay, this is comedy.
Okay. All right. So anyway, so that's what GR says.
I'm kind of depressed. Mr. Slade knows more about GR than me. That's disappointing.
He is correct. It is moving. So if you rewrite the first law, that an object will continue moving through object perceived of as at rest from your reference frame will be moving through its acted upon by another force. That is correct.
Did somebody kick me out?
No, nobody kicked you out.
Okay.
I don't think.
I was booted and I re-entered, but I was booted.
No.
Okay.
Nobody should have done that.
Okay.
All right.
I'm listening.
So apparently, what is going on?
How many eyes do you think an apple has?
How many what?
How many eyes do you think an apple has?
More potatoes really than apples. But if you're having trouble thinking of an apple having a perspective, imagine it's you falling out of an airplane. You look at your accelerometer and you see that you are at rest according to general relativity. But using our imaginations to do thought experiments without having to say, oh, it's a person, diving out of an airlock or something,
But
it's just
the standard terminology, about the apple would be with respect to.
sure. Well, from the reference frame of, I mean, it's from the apple's perspective, from the perspective of an ant on the apple, for example, or whatever. But this is what, as far as I know, what is happening. The geodesic that it's following is not just a 3-dimensional line. It is a 4-dimensional line. It is a 4-dimensional path. And in the direction of time, the apple is moving, along with everything else, is moving at effectively something like light speed. So what happens is when it moves, when it at rest, aka falling in free fall, it is rotating partially out of the time-like dimension and into the 3 space-like dimensions. And as it continues to rotate through those dimensions, as time passes, it picks up acceleration. So that is because the acceleration is the motion of 3 of the 4-dimensional the 4-dimensional path of it being partially translated into 3 dimensions, 3 spatial dimensions.
I'm looking at ChatGPT. ChatGPT just says that there's no energy.
ChatGPT ain't gonna answer this.
Yeah. It just says that it doesn't require energy.
Yeah.
This
well,
type of
so it doesn't, because it already has the energy in the form of its permanent light speed acceleration along the t dimension. So
anyway, I honestly don't like GR for this reason. It's very unintuitive, I mean,
I agree.
The ether model is simpler and explains everything perfectly, including
how does ether explain accelerometers?
I mean, ether is very Newtonian. It's very mechanical. Ether is basically it's Newtonian. It's basically
Okay, so explain why an accelerometer in free fall displays no acceleration.
Well, I mean, there's no force, right? You need to. There has to be a force on the spring. There is no force on the spring in the accelerometer. Why would it show any force? There's no force acting on the accelerometer. Right, this is Galileo's equivalence principle. So Galileo argued, right, Aristotle said that heavier objects should fall faster, but Galileo disproved that with a thought experiment. He said that's impossible because let's imagine a big mass and it falls at a certain rate. Let's now cut it in 2. According to Aristotle, now that each half mass, they should now each fall slower. That doesn't make any sense. So because of Galileo's equivalent, this is Galileo's equivalence principle. So all the forces on the accelerometer as it's in free fall are the same. In terms of ether, right? In terms of ether, so the ether fluid is flowing through the accelerometer, and the ether impacts all objects just the same, including light. From Newton, you see that A equals gm over r squared, meaning but there is no little m. The little m drop.
But the ether has to be able to move through the substance.
It does,
right?
Because everything is waving.
So how does it transmit force while moving through it?
It interacts. It flows through it. Right now it's flowing through me and I'm waving upwards through it. And this interaction, some of it is expressed as drag. Some of it I'm able to flow through the ether upwards, but there is an interaction. It's dragging me downwards. The ether is dragging me downwards. There is an ether flow through me at 11 kilometers per second. And it's dragging me downwards. It's dragging light. It's dragging everything just the same. And it explains why all objects, regardless of their mass, fall at the same rate, including massless objects like light. Everything, because it's a geometric, it's just a fluid. Everything gets dragged just the same.
Okay. Well, I will say this. I don't want to go back into the analysis of the ether model. I was curious about it.
Yeah.
I don't think that it solves the same behavioral issues that we see with general relativity. Stuff checks out like time dilation.
No,
So
time dilation. I mean, time dilation is easy. Time dilation comes out of the ether model in SR, but also in GR. There's no difference. Right now, the ether is flowing through me, so of course there's time dilation. As I'm moving through the ether, or the ether is moving through me, of course there's time dilation. So immediately you get time dilation due to gravity using the ether model. It's a very powerful model, whether you like it or not. It's unbelievably powerful. I mean, I've never seen anything like it. It has explanatory powers. I mean, this is equivalent to like Darwin's evolution. It's like a simple theory that answers everything so mechanically.
well, I think you need to figure out what the affects, how much ether is needed to interact to produce the kind of drag that's causing the motion you're talking about.
Yeah, that's true. Right. The actual interaction, I don't know, but in general, to get time dilation, that's easy. You immediately get time dilation from gravity just because the ether flows, and that goes back to the rubber ducky. The rubber ducky, as you move it in the bathtub, immediately experiences time dilation. So of course gravity creates time dilation. That's easy.
Okay.
And the bending of light, of course gravity creates the bending of light. Of course. That's easy.
Okay, I have to step away for a second.
Okay.
Well, what I was saying, Mr. Slave, is like I have a paper on my desk that talks about an ether in general relativity. I think that would be the place to start if you want to actually start making the theory work out, because they describe how you can have an ether within GR.
Is it
similar to what you're talking about?
Is it a flowing ether? Because Einstein in 1920 had an ether, but he said explicitly it doesn't flow.
No, but what I'm telling you is that it could form a framework for how you could think about ether as flowing.
No, but this paper that you have in front of you, is the ether flowing in this paper, or is it a stationary ether?
Oh, I think it's stationary.
Then that's not my ether. It's completely different. My ether flows. My ether is not the curvature of space-time. I don't even have time. For me, time dilation comes directly out of the ether. I mean, so I never say space-time. The ether model doesn't need space-time. There's only space. Anyway, but yeah, I mean, Einstein believed in the ether. So, like, for people to make fun of people that bring up the ether, it just shows that they're illiterate.
Well, the people that bring up the ether don't believe in Einstein in any capacity a lot of the time.
Right, that's possible.
And they generally just use ether as a magical thing that can do whatever they want it to do without ever actually defining what it is.
Yeah. So I mean, that's sure.
I mean, the ether was perfectly legitimate, very valid scientific construct for a long time, and then it was,
and then Einstein said it's superfluous, right? But then he obviously retracted. But once,
right?
No one cares that he retracted, apparently.
Well, it's hard to unring a bell, as they say.
It's what?
Hard to unring a bell.
Yeah. Everybody likes this magical universe with no ether, in which electromagnetic waves wave through a vacuum, and everything happens in a vacuum. Even though Newton said explicitly, if you believe that the force of gravity is mediated by the vacuum, you need to have your head examined. This is basically literally what he said.
Yeah.
But everybody today, that's what they believe. Anyway, you haven't been here, and I don't think you've been here in a while, right?
I was asleep
For 2 days.
yesterday, but no, I slept for a while though. I slept for like 14 hours.
Yeah, because this server has been very unkind to me.
Yeah, it has been.
Yeah, the people here are like really bored. Are really boring, not just bored and boring. But maybe in time. Anyway, so today I'm trying to have productive conversations with people, and it's like pulling teeth. They are unwilling to have productive conversations. Like I want to talk about physics, and they want to talk about nonsense.
I think you should give me edit rights to your document, and then we can talk again.
No, not doing that again. No, I don't want to waste my time.
You know you want to, Mr. Slave.
No, I definitely don't want to.
Comments like last time.
Yeah.
Yeah, they destroyed the documents.
I'm really disappointed that Mr. Slave knows more about GR than me. I think that
I don't know who are you? Are you Gamma?
what? What do you mean?
I don't know who you are. Why do you keep talking about that?
Yeah, I have a question.
Why do I keep talking about that? Because I'm realizing that you know more about GR than me, and that's sad.
But what do you mean? Like, what do you think? But like, all I'm doing for the past 2 months is studying physics around the clock. And
Clockwise or counterclockwise?
and all my life I've been listening to lectures online. Like I'm trying to figure out like physics since I'm little. So anyway,
Jesse, you had a question, right?
Oh yeah. Does anybody know if Geo has come to grips with the fact that there's a 24-hour and southern sun in Antarctica, or is he still bucking that?
Oh, I don't know. I've been timed out, so
They're not believing that till they go.
wait, Gamma, do you know any quantum mechanics?
He said he's timed out. Oh.
Gamma said
Who,
he's
me?
timed out.
Yeah.
yeah, I'm timed out.
What does that mean?
You can time people out on Discord for breaking the rules, which in my case was excessive personal attacks.
Who?
On a particular individual.
Gamma?
No, me. I'm timed out from Earth Awakenings for tormenting someone in the text.
Oh, okay.
But the funny thing was that guy has me blocked, so he opened all of my messages just so he could screenshot them and send them to the mods to get me timed out, which is pretty funny, if you ask me.
Ordwan, did you hear my question earlier about speed versus acceleration?
No.
Well, they were talking about the apple falling out of the tree, and I was saying that I feel like every time we get into the context of, reference frames or stuff like that, I only ever hear acceleration come up and not speed, and I'm wondering why that is.
Well, speed comes up a lot in talking about reference frames in special relativity.
What's
that was that's the whole point of the train paradox problem in special relativity, which got brought up in our Alan and Shane. Like in special relativity, velocity is extremely important. It's just in general relativity, we speak more about accelerations generally. I'm not sure.
Yeah, but I don't get that because, I mean, that's just to say something's not accelerating is not at all to say that it's not moving.
Yeah, well, sure. But with respect to the idea of inertial and non-inertial frames, that's where it comes in. So an inertial frame is one that is not experiencing acceleration, and it behaves differently than a frame that is experiencing acceleration, which would be non-inertial.
Yeah, but okay, I kind of get what you're saying, but when you're talking about the idea of whether or not something is moving, the experience of the whichever frame you're in doesn't matter. It's either moving or it's not.
How do you know? How do you know if something is moving or it's not?
How would you know?
Yeah.
Yeah.
All you know that it's moving in reference to you.
Well, everything is in reference to me. I am the observer of my own consciousness.
Well,
so
okay.
when we're having a discussion, I don't get where the reference would be outside of anyone.
Okay. So what's your question? Maybe I can help you. What's your question?
My question is, when the topic, sometimes when we get in the details of what is moving towards what or what is moving at all, I always hear acceleration brought up, but not speed. And I'm saying that acceleration has nothing to do with whether or not something's moving.
Well, so in special relativity, we only analyze motion without acceleration. So do you have a question about special relativity, about motion without acceleration? Like that in special relativity, all we have is velocities. We don't change velocity. We have constant, everything is moving with a constant velocity. There's no gravitational field, there's no forces, there's just motion. So, do you have any questions about that?
I don't think I have a question. I don't think I have a question about the models themselves. I just have a question about why only one portion of it is brought up.
What do you mean one portion? So usually the discussion is split. In SR, special relativity, we don't have gravity, we don't have forces, we don't we don't accelerate, we don't change velocity, we don't change direction. We just have constant velocities. Things are moving in reference to each other at constant velocities. That's one type of discussion. And then there is the GR discussion, where we also have everything else: forces, gravity, acceleration, change in direction, anything you want. So,
right. So for SR, that's I think that's kind of the point I'm getting at is when the topic is about what is moving, when you just bring up
hold on. Just let me stop you. That doesn't. In SR, there's no such statement. What is moving? That's undefined in SR, and also in GR. You can't say what is moving unless you use the word relative to. That's why the theory is called relativity. You always have to say or imply relative to. Who's measuring? Who's observing? So you can't say moving unless you're saying relative to. Who relative to who is the observer?
Right, but that's my whole point though, is I don't get why that. Okay, I understand the concept, right? But when you're talking about whether or not it's true if something's moving, whether I observe it or not, just because I'm not in
it's undefined. For something to be moving in SR is undefined. You have to always specify in reference or relative to whom. You have to, otherwise it's just undefined.
So there's no absolute truth of whether or not something is moving.
Correct. That is exactly, that's why it's called relativity. Everything is relative. Everything must be expressed relative. Yeah. Go ahead.
Maybe I just failed to grasp the I don't know the correct word here. Like I said, when you're having any discussion, everything should be relative to the observer, right? To any observer. So I don't get why that's even a factor.
Okay, then fine. But there's no absolute truth about motion in relativity. Yeah, I understand what you're saying. You're saying we don't have access to absolute truth ever. Fine. That's also true. So relativity is a modern theory. You could say that maybe God, in reference to God is the absolute truth or something like that. I don't know. But relativity is a godless theory. There is no absolute truth. Everything is relative. So fine, then you understand it. But what's bothering you?
Well, I feel like when you put it that way, it seems more kind of philosophical than scientifical.
It's philosophical. It's about it's understanding the universe. It is the way the universe works.
Philosophically.
No, we test the universe and we know that the universe abides by special relativity. We know that the speed of light.
But what you're telling me is
I'm trying to think what is an experiment. I think even magnetism is due to relativity.
what? Magnetism?
Yeah, but I'm trying to think of an experiment that we can conduct and validate SR. Muons. You can what? You can detect.
I'm gonna step back in here, but you let me know if you think of something.
Muons is probably the best one.
Yeah.
Ooh. I'm gonna go to sleep again. But see, we can have productive fun conversations and not just spam Nazi memes.
This is the exception. I've spent so many hours on this server, and the people were completely unwilling to have a conversation about anything except for nonsense. They just wouldn't. No, there was nothing I could do. It was like war. But wait a minute, Sea Lion, why do you keep going back to sleep? Are you sick?
No, I just had too many days that were sleepless last week, so
I see.
Yeah, I stayed up for like 36 hours or something.
Amazing. Okay.
Yeah, so yeah. See you guys later. Bye.
See you later. Does anybody else have any questions about SR, GR, quantum mechanics, dark energy, black holes, the wave function, the wave equation, Heisenberg, Schrödinger, Bohr, Planck, Einstein? No? Okay. All right. Anyway, these were good discussions. Some of these discussions were very good. Let's see. Oh, there's no one else. Oh, everybody's leaving. Okay. Let's see what's going on with Flat Earth. Hello.
Yo, what's up? I'm still here.
Hey, what's up? What do you want to talk about?
Yeah, man, fire it up. I'm just kind of listening at the moment because I'm doing a few things, but I'm listening. There's people on the live streams too that are always listening. So, and people will, if they hear people talking, they'll start joining in.
So
You got a topic or something?
yeah,
Who
I
else is in
mean,
here? Yeah, whoever wants to jump in.
I believe
What were we talking about? I was kind of talking earlier, but then I had to step away, so I don't know exactly where everything went.
I wasn't here. I was on Globe Gangsters for a while. Anyway, so I believe in big physics, except for I believe in the ether. Does anybody have any questions about?
Right on.
So does anybody
Hey,
have
dude.
any questions about big physics? Does anybody want to challenge big physics? Because I represent big physics.
How about small physics?
That too.
That one too?
Yeah, but
Medium? Medium
yeah,
too?
all of them. any mainstream physics.
Supersized.
Yeah.
Supersized physics?
Yeah. I agree with mainstream physics on everything except for the ether. So everything for me, the universe, there is ether.
Say what?
Yeah. So I agree with everything mainstream physics says, except for there is ether. There's an ether fluid that fills the universe, and everything else is just a wave or waves or wave packets.
I mean, I can understand why you don't, but why don't you
Mhm.
personally believe that there is no ether, though?
I do believe that there is ether.
Oh, you do believe?
Yeah. I'm saying I agree with big physics on everything, except for I believe in ether. Big physics doesn't believe in
Oh,
ether.
okay. I heard you wrong. I'm sorry, honey. I heard it backwards. Okay.
Yeah.
Okay, in like a geocentric globe scenario, or are you heliocentric, or are you like planar, stationary, flat? Like what?
I'm vanilla. I'm mainstream physics. I agree with mainstream physics. So the
So wait,
Earth-
a globe Earth with mainstream physics and ether.
Yeah.
I'm just trying to.
And vanilla.
Yeah, I'm vanilla physics.
Cookies and cream.
So I'm super mainstream when it comes to physics, except for the ether. So my ether it causes gravity, it causes electromagnetic waves, it causes quantum mechanics. It's the underlying field of this universe. This everything we perceive in our universe, these are just affects in the ether. The ether is the only.
If you
Mhm.
go ahead.
What?
Quit interrupting, Jeremy. Quit
Yeah, my bad.
interrupting.
He
It's
stopped
so
talking
rude.
for 1 split second, so I thought it was my turn to talk. Go ahead.
Split minute second. I'm just messing.
Jeremy, you have said enough.
No,
That is-
anybody can jump in and ask
You're
me.
past your allotment of words.
But dude, if you believe in all the mainstream physics, why were we arguing yesterday over whether general relativity says gravity is a force or not?
Question mark, right?
I mean, whatever.
That's a whole.
You mean what? Right. Question mark, right?
Whatever. Whatever.
That whole path is a water slide with cayenne pepper sprinkled down the whole way.
Whatever mainstream physics.
Sriracha.
So whatever mainstream physics says, I agree with it. I'm not denying mainstream
Of
physics.
course you do. Sorry. I'm sorry.
So mainstream physics says that GR says that. Oh, GR says gravity is not a force. Right. Mainstream physics says gravity is not a force. But
But you were arguing with me
yesterday.
yesterday. You were arguing with me yesterday that it is a force now.
So is
No.
it a force or is it a force? What do you think it is? Not what
No.
mainstream or authority says. What do you think it is?
Well, I think
He thinks what the mainstream thinks.
Ah,
no.
question mark.
No.
And
No.
also,
No, I don't.
you,
So I don't. I
mainstream
disagree.
phys-
I disagree with
What's
mainstream.
up, Rick?
So since in my physics I have the ether, and my ether is gravity. I have gravitational ether.
Is it your ether or my ether? Or
My-
our ether? I just want to make sure that.
It's my ether theory. So my ether theory, ether is the cause of gravity, and it's mechanical. So yeah, for me, gravity is a force, definitely.
Oh.
are you geocentric? Because mainstream science says you're at the center of the observable universe, right? So, and then if you got ether, you're heading towards the geocentric stuff.
No, I'm completely mainstream. I'm completely mainstream.
He said, "Hey."
You're not completely mainstream, bro. You're talking about ether, for God's sake.
I'm
I
completely.
do like it though. I do enjoy the conversation that he's put forth though. Seriously.
I'm completely.
Yeah, I don't mind. It's just inconsistent.
Yeah.
I'm
Go
completely.
ahead.
Can't be mainstream, mate, if you're talking about ether.
It is very mainstream, but he's saying though it's very mainstream. He said, "I believe in mainstream physics." He said, "I believe." The keyword, I believe, honey. What's the knowing though for
No,
your
no.
mainstream physics?
I
That
agree.
you're acquiring
No, I agree.
everything for.
No, I
You
agree.
gotta have
faith. I agree with mainstream physics, except
do have faith.
except for the ether. So my
Ah.
ether causes
My
gravity.
ether, your ether, our ether, right?
Yeah.
My ether causes gravity on all levels. Does your ether? Does my ether cause gravity and your ether causes a different gravity? What's the difference? Like seriously, dude.
No. My
I'm joking
ether
with you.
theory.
My
My ether theory is gravity. It causes gravity. It is the machine.
Okay,
It is
so it's a force now. It's become a
Yes.
force. Your ether has become a force. It's a gravity of something bigger than you, a force that you can't explain. It's a force now.
in my ether theory, gravity is a force.
Okay, gravity is a force in your ether theory. What is ether?
Ether is a fluid that fills the universe, and everything that we consider matter, like particles, those are just waves. Those are just waves in the ether. So there are no particles.
You know, space-time basically. Well, ether basically displaced. What is it? No, sorry. Space-time basically displaced ether, right? Is that a correct interpretation?
I mean,
I don't know.
to their interpretation, but to my interpretation, no. Right. It depends how you want to break that down.
The idea, they brought in the space-time thing to
Okay.
to save the whole model.
Correct. Yes.
Because they didn't want to reveal the ether because
Mhm.
yada yada yada.
100%. That's the only reason why they did it. So the ether is real, but you want to discount it, but account it for when you want it to account. Or wait, am I mistaken here? Am I talking to a flat earther or a glober or a non-deciding person in the moment?
Who, me?
Yes, you, sweetheart. Yes, you.
I'm completely.
Give us your details.
I'm mainstream. I'm.
It's like age, sex, location, ASL. Like it's like one of those moments again.
Anyway,
I
so
don't know, cosmology, moon landing, and 9/11. Give it to us.
Exactly. Ain't your freaking thing,
I'm
right? What's your role?
I'm completely mainstream. I'm completely mainstream.
Oh no, honey. That's like the worst thing you could say on the server. I'm completely mainstream, y'all.
Except for the ether.
Except what?
Except for
How
the
can
ether.
you be? Okay, the ether you can actually not even show. You can't even prove, but you can prove all the things around you in the world. But you're telling me you're only gonna say the ether, huh?
Where I lost you. You.
I like ether though. I do like ether, but you can't prove ether. You can't prove ether to me.
Yes, I can. I have.
But I do
two-
like it. You can?
Yeah.
Okay.
So according to my math.
Math. I love math with an S.
According to my math, Michelson and Morley should have gotten. Should have received a null result, just like they did. So I can explain why they got it, why they got the null result.
You can explain why they got the null result of all people. You can.
Yes.
Okay.
And they would have needed a much bigger interferometer in order to detect the ether. It's more like 10. They used a 10-meter arm interferometer. They would have needed something closer to 10-kilometer arm.
Do we have that?
I came up with an experiment. Yeah.
You can't.
Yeah, it's possible.
Do we have that? Do you have that? Oh wait, do you have that then?
No, it would cost about 100,000. It would cost.
Wait. On a theory, or you think, or like, can this happen? Or it's just like a conception in your head. Like, I think I could build this and it might happen.
No,
I'm trying to prove ether right now.
Yeah. So I can definitely build it.
I like ether though. I do. I actually believe it exists. I want to make it very clear. I think ether is real. I can't prove it to you. So if you could prove it to me, this is like some learning experience right now, honey.
Right. So there's many ways to prove it, but there is at least 2 experiments I can provide, or maybe even 3 experiments I can provide to verify it. Like the first thing would be to finally do a correct Michelson and Morley interferometer experiment. So we just need a bigger.
Okay, what's the correct one and what's the incorrect one? So you're going to claim there's a correct one, and the first one was the incorrect one.
So
how was it incorrect?
It was incorrect. It was.
Can you tell me?
Yes, it was incorrect. It was just too small. They used a 10-meter apparently.
That's it.
It's too small.
Okay.
So you need a 10.
So you think you need what?
10 kilometers instead of 10-meter arm.
Why do you think that instead?
Well, the longer the arm, the slower the ether motion that you can detect. The more sensitive you are to the motion of the ether, to the velocity of the ether. Michelson and Morley set out to detect the velocity of the ether, to measure the speed of the ether. They assumed it's about 30 kilometers per second as the Earth is moving through the solar system at about 30 kilometers a second. But that's assuming that there is some ether wind. But according to my theory, there is no ether wind. Ether is gravity. It's flowing right now into the center of the Earth at a level.
Gravity saved you again. He pulled you back from reality. He said gravity.
How are you
Go ahead.
conflating ether? How are you conflating
I was right
ether
there
and
with
gravity?
him.
That was
I was right there with him. He said gravity, and my whole soul said, "What?" Okay, show me your gravity, because I'm with you until you said gravity. Man, what is wrong?
No, chill out.
6
Getting
years,
stressed over this
gravity,
shit.
gravity. Come on, I was right with him, and he said gravity, though. Come on. I thought you were like with ether. You were on that same conversation. You believe in it. Like physics doesn't get it. I believe in everything mainstream but ether. Like ether is another exception that most people in flat earth don't even believe. They go, I can't prove that. Okay, now you're going to say, I'm going to prove that. And then you said gravity. That's where I go, what? Gravity is a theory. Gravity is something you are claiming as a force that isn't a force. That is a force. It is back and forth bullcrap. The mainstream feeds that you say you don't with ether, but then you went to gravity. That's where I have a decompartmentalization going. What did he just say?
What's the question?
If you guys want to accept that, that's fine. But if you want to say ether, and he's accepting ether, he's accepting ether.
What are you talking about?
It's pulling
I don't
gravity
know.
in.
Yeah.
Anyway, so
Let the real woman talk. Ah, get it?
anyway,
Okay, prove gravity. Okay, you must have gravity. Prove gravity.
what do you mean?
Ether's gravity. You want to prove gravity compared to ether.
No,
Prove gravity.
no, I told you I agree with big physics on everything except for ether. So I agree that there is gravity. I don't deny gravity. I assume
So you don't deny gravity.
correct.
So gravity is a force.
In my ether theory, yeah, gravity is a
Correct.
force.
What is the force?
What is a force?
No, what is the force? Not what is a force. What is the force?
I mean, it's whatever causes the apple to start accelerating towards the ground. Something is pushing the apple towards the ground.
Pushing or pulling?
Pushing, pulling. Something is
There you go.
forcing, some force is causing the apple to accelerate towards the ground.
Okay.
Is that ether?
What's that?
You're saying that's ether?
There we
Yeah.
go. Thank
Yeah.
you.
In my ether theory, the ether is flowing into the center of the earth and is dragging everything along with it.
So everything they tell you, mic drop, gravity, boom, is ether now. I listen. That's
Where-
almost like
where-
accepting gravity to me.
I got a question though. Where's this ether going to? Why is it going to the center of the Earth? Are you saying it's also going to the center of the sun? What's going on?
Yes. So the way the ether works, the ether, anytime the ether interacts with any particle that we call a massive particle, like an electron, then the ether self annihilates. Now, during this interaction, the ether imparts mass to the electron. So the electron initially does not have
What?
mass. Right. So the ether interacts with the electron with the Higgs mechanism. So the Higgs
Did you listen to Terrence Howard? Did
No.
you watch Terrence Howard on Joe Rogan?
No.
Well, it's like the only time I ever heard them try to like mix the ether with the globe. They're like trying to steal the ether from us and like keep their globe. And I feel like I don't know, you're jumping on that train.
Oh, they've been doing that for a minute.
Oh, really?
I got a question.
Trying
Where's all this
to trying to
ether?
re-steal the ether. Yeah, they already did it with all of quantum physics, and then now they're even doing it more so. They're trying to have a dog in the fight because they know it's everything's headed back to. Well, yeah, because if you have a stationary Earth, you still have to account for the effects that they claim are accounted by the Earth rotation. So that's where the ether is like the connecting point, that there is motion. It's just not that because we're on the outside of a ball. It's just because we're inside of a crystal ball of sorts, and we're on a huge stationary planar surface surrounded by this structure.
Man, I got a question for the gentleman. Where's all this ether coming from, and where is it going, and where is it gathering? What's going on? If it's traveling into the center of the Earth, right? You call it a ball. I'm just wondering, how does it, like, where is it all gathering? Is all this ether building up at the center of the Earth? It's all going to explode one day? What's the go?
So the ether annihilates when it interacts with any massive particle. And through the interaction, it imparts mass onto a massless particle. And that's how the electron has its mass. And that's the Higgs mechanism. But
Where's the ether emerging from then?
So the ether, I'll just finish the thought and I'll explain. So the ether annihilates whenever it interacts with any massive particle, and therefore an instantaneous vacuum is created, or low pressure. The rest of the so very quickly, all the ether in the universe should get swallowed up by all the massive particles. So for
Where is it coming? What are you saying, that the ether is just there and it's getting used up, or are you saying something's creating it and then destroying it?
yeah, so the universe should have collapsed on itself. So that's why Einstein added lambda, and lambda is the creation of ether. And so ether is always spontaneously creating more of itself and is naturally or spontaneously creating a positive pressure. So there is always a
So you got something coming from nothing. Yeah.
you could say it's dark energy. So as I said, I don't disagree.
Dark energy.
Yeah. So as I said, I agree
Okay.
with. As I said, I agree with mainstream science. So mainstream physics.
So then why don't you call it? So then why don't you call it quantum physics and stuff? Like why? Like they're kind of like they don't want the ether. Like they replace the ether. So why do you think those things go together? The ether replaces everything in their, almost everything in their, like, you know, their physics, their astrophysics or whatever.
So my ether theory explains all of physics. Basically, it explains special relativity. It immediately gives you special relativity. It gives you gravity. It gives you quantum mechanics. It gives you particle wave duality. It gives you dark energy, black holes.
But they're the complete opposite. I don't think you understand like what the, like, what is this, like a different ether than like the one that like Tesla like talked about? Or
I don't know Tesla.
you don't know Tesla? Yeah, I don't know why you're using. Can you use a different word for your thing?
I can use any word, but in general, you know, it's ether, because my ether is also the luminiferous ether. I'm just saying that it's also gravitational ether, but it's also quantum mechanics. It's the quantum mechanics field from quantum field theory. So it's the field in which all the elementary particles pop in and out of existence. So all of quantum.
Yeah, but it's, I mean, quantum physics is like literally like the opposite of like the etheric like model of like, you know, particle, like atomic particles.
No. Okay.
Yes.
So, well,
why do you say that?
My ether.
It's the opposite. One is literally a wave in the ether and no particles, and one is particles and they act like a wave sometimes, which is like just stupid, really.
Right. So it's, as you said,
That's not correct.
As you said, it's stupid. So in my ether theory, there's only waves. There's never a particle. The only particles that exist in my ether theory are the particles that make up the ether. But it's a fluid. I don't really know what makes up the ether. But everything else that we know, like electrons are just waves in the ether, just like quantum field theory says. So my ether theory predicts quantum field theory. It predicts gravity. It explains gravity. It predicts or explains special relativity, dark energy.
Okay. Does your light also then need, does it need a material aspect to it then? The photon or the proton?
I couldn't understand you. Could you please repeat slower?
The what's going on with your theory on light then? Is it a particle?
No, there are no particles. So a photon is a wave, just like de Broglie and Einstein said that, there's no particles. It's just waves, but these are waves that don't spread. It's not normal waves. These are wave packets, but it's still waves. It's still the ether waving. So a photon is the waving in the ether. It's a wave in ether. It's the ether waving. There's no particles.
Okay. Perturbation of the ether. Yep, got it.
What?
A perturbation of the ether. I think that's correct, huh?
I actually don't care.
Yeah.
Actually, I don't care, honey. I actually
Well, that-
love you. You're a good person. I don't care. I mean, we're fighting
Well,
over some bullshit. I don't care what shape of the earth. We're joking about some ether or not ether. I was a little harsh on you. And now you're being a little harsh on him, if I'm going to be real with you. Like, you want to be harsh?
What's going
Like,
on?
let's be real. Because I was
Stacey,
being real
what the
with you,
fuck's
and you're
going
like,
on?
what's wrong? I'm not okay. That's just
What are
real.
you talking
I'm not
about?
okay, Rick. Rick, I'm not
Okay.
okay. Rick,
But you're on a live stream though.
I know.
What are you not okay about?
Life.
Okay. You wanna bring that in here? It's up to you, but I mean.
No, I don't, Rick.
Okay.
But what I want is y'all to be real. You're talking about some fucking ether that you can't even freaking explain or show. But he's talking about some shit that's like, when I try to explain it, no, it's not okay. But when you want to, it's okay. He's talking about some
Who?
mainstream shit.
I don't know what you're angry about, Stace.
Everybody.
Yeah, I don't know what you're directing it at, who you're projecting it at.
Yeah,
I'm a
we're
bit
just having a
confused.
conversation about like.
No, you know
the
what?
ether.
Cuba and Rick. You're right. Thank you.
Anyway, does
It's
anybody
kind of. What's up?
does
Oh,
anybody
he's stealing the ether from us.
He's laughing a little bit, I feel.
Dog, he's stealing the ether from us and calling it gravity.
Mixing
all
in- he's
good,
not
though.
stealing anything. He's mixing
I'm
his
playing.
like two like theories together.
Well, it's many theories that fit together. You could say it's a unified field theory. It's a theory of everything.
But they
I feel like you're laughing, bro. Like you're getting everything and mixing it into this sort of collage of, like crazy stuff. I don't know. I mean, you're more than welcome to do it, obviously.
So hold on, let me ask him a question. So the ether attracts things to the center of mass.
The ether doesn't
said-
attract anything. The ether flows from high pressure to low pressure. So in general, there is high pressure ether everywhere in the universe because of dark energy, because of spontaneous creation of ether. So there's everywhere positive pressure of ether. But whenever ether interacts with a massive particle, it annihilates, it self-annihilates, and therefore an instantaneous vacuum is created, or a low pressure. And then you have a gradient of pressure, and then you have a flow of ether from high pressure to low pressure.
No, yeah, listen, I actually agree with that, with the pressure mediation.
No, there's no
and the,
mediation. There's no mediation. It's just
there is so how would you have pressure without mediation, dude?
no, there's just flow.
See, I think you haven't actually hold on,
No.
respectfully, I think you haven't really fleshed out these concepts. I think you might be actually new. You might have been watched a couple videos in like a month or two, but you sound pretty like novice. Like the other day when you were trying to explain the Coriolis effect, you failed horribly, dude. So before you move on to ether and ether physics, at least get like the fundamental basics down pat, right? Like Coriolis. Respectfully.
Yeah, I don't
Because
know.
now you're saying that
No
you're
offense,
talking
yes.
about pressure, but you can't have pressure without pressure mediation.
I
You
don't know.
realize that, right?
I don't know what you're
Thank
talking
you.
about. So
Where did you come from? Yes, God. That's where you came from.
anyway, so
Puerto Rico, apparently.
you just have right when you have like in fluid dynamics, if you have high pressure area and low pressure, so you have a flow from high pressure
What is
to low
that?
pressure.
What is that? What is that? That's pressure
Ask him again.
mediation.
One more time.
From high to low, dude. That's literally pressure mediation. And you're saying
No.
that there isn't any of that.
No,
but yet you're describing it.
No.
So to me, that just shows your ignorance. And respectfully, bro, like before you come in here, at least get some of these concepts fleshed out.
No.
Because you're gonna sound silly.
No. There's just a pressure grade. It's called a pressure gradient. It's just different levels of pressure. And you have a flow. You have an ether flow, a fluid flow from high pressure to low pressure. So the Earth then becomes, the Earth itself is a low pressure zone of ether. And that's why there is flow of ether into the Earth. And this flow is going through the apple and is dragging the apple towards the Earth. And that's gravity.
Yeah. I agree with that. I actually agree with that part. That part I agree with.
I don't
There's
think
a
you
downward
do, though.
vector. There's a downward flow. You can actually measure it. Yeah.
That's
100
gravity.
volts per meter.
But his like ether, I don't know, like if he's talking about like electricity, and I
Well,
don't
this is
know,
what
like his
Isaac Newton
That's the key. Yeah.
Newton described it that way. An ether flow. Isaac Newton himself, a flow of
Yep.
ether that was coming down from above down to the earth. That is part of why the gravity effect.
But he doesn't believe in mainstream
No,
ether.
Newton.
No mainstream ether, he said. No,
Newton-
no.
Are you
Yep.
Isaac Newton ether? Are you an
There you
Isaac
go,
Newton
guys.
etherist?
No,
Now you're hearing it.
Newton didn't talk about ether as a force of gravity. Newton
Oh
actually,
yes, he did. Oh, he absolutely did.
I love you. There we are.
Anyway, does anybody else want to talk about my theory?
No, it's your theory, not our theory, not anyone's theory, just yours. So how can I talk about it? It's just your theory.
Do you have
It's not mine.
questions? Do you want to ask me questions?
Oh, actually, if you could write it down for me and put it down in a theory, like an actual a planogram, I might actually follow it.
Well,
Dude, it's right. It's right in the Principia for Isaac Newton talking about this. Here, this is a description of it. He renounced standing attempts. Okay, here, I'll just read from here. He calls this is Isaac Newton. He calls this intervening medium ether. In his ether model, Newton describes ether as a medium that flows continually downward toward the Earth's surface and is partially absorbed and partially diffused. This circulation of ether is what he associated the force of gravity with to help explain the action of gravity in a non-mechanical fashion. This theory described different ether densities, creating an ether density gradient. His theory also explains that ether was dense within objects and more rare without them. As particles of denser ether interacted with the rare ether, they were attracted back to the dense ether, much like cooling vapors and water were attracted back to each other to form water. In the Principia, he attempts to explain the elasticity and movement of ether by relating ether to his static model of fluids. This elastic interaction is what caused the pull of gravity to take place, according to his earlier theory, and allowed an explanation for action at a distance instead of action through direct contact. So that's from Newton himself.
Could you post a link to that in the site?
Sorry. Forgive me. You. We've been here for like 6 years. He said post a link for that.
Yeah, but to be fair, that was Newton.
No,
Newton did have a,
Koshi, you are not going to come in at this specific time.
Thank you, Stacey.
This is why I want to
Thank you,
leave
Stacey.
you. No,
No, yeah.
no, Koshi.
Thank you,
No.
Stacey.
What's going on?
No.
I'm not sure.
No.
Here, I'm posting.
sick and tired
Hold
of
on, guys.
fakeness.
Hold on.
Go
Let's
ahead.
go one at a time. I'm posting the source for him right now. All the sources right there.
Thank you.
I was just gonna say, yeah.
Go ahead.
Yeah, Joe, because you're. Yeah, so I was gonna say, yeah, Joe. You're right that Newton did have an ether theory that was described like that, but I
You
don't
have
think
a lot
that
of
was in the
theories, too.
Principia. Please, Stacey. I don't think
will.
that was in the Principia, though. I think it was
No, it's
a
all in
separate
yours.
paper he wrote.
Not your paper.
Where are you posting it?
Indians.
Kosho, I thought you would have been an ether advocate.
This is why it's important for people not to talk during other people, because I don't know where you got that from that I was or wasn't in what I said.
I would have
But it was
thought.
probably
I said
because
I would
Stacey
have
was
thought.
talking through when I was talking.
Because people
Yeah,
speak
I
the
know,
truth
I know,
and you
but
don't
I
like
know,
it
but
after so many years and you get sick.
Okay.
Right,
One sec.
Kosho?
Stacey,
Stop.
just do everybody a favor and
Let's
just go on
Do
mute for a second.
everybody a favor and stop being here and participating in some bullshit that you don't even want to. Because you're like, I'm a
I like
flat
Kosho
earther.
here.
Tomorrow I'm not.
Kosho's a good ball to
Today
bounce
I'm
stuff
not.
off.
But how
All
is
right,
a
let's-
good actual flat earther today a flat earther because I asked him to be? Kosho, will you be a flat earther? When he's in his right mind, he'll go, yes, baby, I'll be a flat earther. What I mean, serious. Gio and everybody who's been here, are you serious? With
Okay,
Kosho,
Stacey.
he's a mod.
Just Yeah, sure. I mean, that's fine.
Jim
I'm
Panda.
What about it? So,
Right.
Stacey, I don't know
It
what's
should be
going on.
question mark, question mark. If you're talking about good and evil, question mark, question mark. You guys talk about this every fucking day. I do. I question myself every day. I look in the mirror
Make sure
every
you-
day. Mm-hmm.
Okay, Stacey, make sure that
What?
you want to be here publicly doing this right now. I'm a little
I
bit
do
concerned.
actually.
Okay, that you
No,
may
you can
regret
be
it.
you can be concerned. I won't regret it
to you.
because I never regret the truth.
Yeah.
I never regret the truth.
Well,
Even if it's brutal.
But
It's brutal, but it's honest.
Well, can we just?
Okay, I just won't stop. I'll just stop
Gio.
you.
No,
you do your
Gio
thing.
will better work with me. Trust me. By
Well,
you
let's
coming
just.
in.
I think we were
Because
on a topic,
I
right?
need to know why you're doing this, Gio.
Let's
Why
just
are you
get
doing
back to the
this?
topic.
No, why are you doing this?
Doing what?
Uh-oh.
He's the resistance, Stacy. You know that. It's
Mhm. You have Koshi, who's sit here, betrayed me with Quantum Eraser, right? 24/7. You came here with me in the beginning. I got you, Stacy, when they all betrayed me, right? I got you. Don't worry, Stacy. I got you. And then we got Koshi here, who's sitting here, who sat here in Texas, who would not meet up with any fucking experiments, right, Riggs? Anything when I was in Texas, wouldn't do nothing. I was there, but nothing. And then he made it with Space Pope. Space Pope, that actually is a cool dude, but he's like, Koshi, you full of shit too. So why are we entertaining Kosho? Which I call Koshi because you a fucking Yoshi. I'm here for fucking truth. You're here for entertainment.
What
This
did you
Earth
do,
Awakening.
Kosho?
No,
What
Kosho, what do you do?
Kosho?
Yeah, I
What
met
did
you.
you do?
I tried to
Koshi,
meet
what you do to her, dog?
How many people have tried to meet you, and you sit here on a Jim
Kosho.
Panda server, talk shit. You want to act like you're my
Kosho
friend
seems
at a
girls
server.
mad.
No, let's talk about Kosho in a DM.
I think Kosho's
Ding, ding,
cool.
ding, ding.
I like
Riggs is
Kosho.
a
I
beast.
don't know why
No,
we're
no,
talking
no,
about
he's
Kosho. How
not.
about
No,
you,
he's
Jeremy?
Hold on,
not. No,
guys.
he's
Hold on,
not.
Stacy.
I
Stacy,
know.
hold on. Just stop.
You
and
want to
let
be
him go over
real?
it.
You want to be
Stacy,
real though?
stop. Stacy, you gotta chill for a little bit.
Oh,
We're on a
shit.
topic. Let him go over to Ether. All right.
Okay, so
Yeah, it went from
I'm
the subject
reading.
to personal for some reason.
I'm
Jeremy,
reading.
that's how you treat ladies? Holy shit.
Yeah, dude, you make him mad. What did you like? What?
That was Kosho. Kosho fucking hit it.
Oh,
quick.
just get back to it, guys. Right, the Principia. How do
Yeah.
you say that weird word? I've heard it with a hard C. All right, let's get. You know what's up?
I was just gonna say that it's true because he did have an interesting ether theory that
Ooh.
sort of like it sounded almost kind of like Einstein's, general relativity almost paralleled it in some ways. But either way, all I was saying was that he did have that, but it wasn't part of the Principia. It was a separate paper he wrote like later on.
He's mixing ether and quantum physics, and quantum physics like has like a bunch of fields that have like no electricity that you can pull from them. Like it's just it's just not the same thing.
I mean, we don't know that. Right? We don't know that yet.
That's like the whole quantum physics fucking rabbit hole. They'll never get anywhere. 'Cause they'll never lead them to how you pull electricity from the ether.
Quantum physics is something that they're still it's mostly theoretical, right? But
It's completely theoretical. That's the point. It's not.
but so is
it
ether.
It avoids finding out what physics really
bro,
is.
Hold on, but so
The
is
ether's
ether.
not theoretical, bro.
Yeah, it is. It's metaphysical.
How
dude.
so?
It's because it's
Yeah,
metaphysical.
tappable. You can
it
tap
can't.
that
It's
shit,
not
it's easy,
bro. Hold on, dude.
One sec.
So right now, can you tangibly possess ether?
Yeah, you can tap from the ether.
One sec.
How?
Can I tangibly what was the terminology? Possess light?
Yes.
Can I do
Yes.
that? Can I do that with light?
No, but you can. Light is physical. Light's considered physical according to philosophy, right? It's
Sure,
measurable. It's
philosophy.
observable.
How
The
much does it
ether-
weigh? How
the
much does it?
ether-
What does it
Hold
feel
on,
like?
bro. Hold on. I'm trying to elaborate on an idea here, and you keep interrupting
Yeah, sure.
me, bro.
I'll
'Cause
play with you, bro.
You have to at least
All right. Okay, let's watch TFM.
Terminators did, and then you had the approach this enemy like it's the classified and it's open. I guess you can't just rely. People are going to be like, oh. All right, welcome everyone. Happy Saturday. This is Turd Flinging Monkey. Welcome to the Turd Flinging Monkey Show. Shogun is here, but he's in his car and he's on his cell phone, so he can't really talk. He might pop in. I'm mostly flying solo. HD said he's got a thing tonight, so he may be late. I don't know when he's gonna get here or if he'll just take the night off. We'll see. We have a lot to talk about. Now some people are gonna be like, oh my god, I saw on Nick.tv when I was like putting on the stream. People were like, oh, it's gonna be a Black Pill stream because the head of Hezbollah, not just the head of Hezbollah, like all the leadership, were all in this secured underground bunker, and Israel hit it with a bunch of bunker busters, which are literally missiles designed to penetrate underground bunkers. Like that's why you need air defenses. You can't just rely on underground bunkers unless it's like in the side of a mountain. Like, like if you're in a mountain, you're fine. But if you're just like in a fortified building, we have missiles that can destroy those. That can basically blow the shit out of reinforced buildings pretty easily. So that's exactly what they did. And they basically killed all the leadership of Hezbollah. And I was like, okay, what's hilarious is this morning, I go on YouTube to see what video has been posted by, because I like to get both sides. Obviously, with the mainstream media, you get the pro-Israeli side pretty definitively. But I like to follow certain content creators and certain news outlets, which kind of give me the other side. So I'm okay, what are the Iranian, Russia, pro-axis of resistance guys? What's going to be their take? Because they've been putting out this shit like, oh man, Hezbollah has been embarrassing Israel, and Israel's going to be defeated because they can't win. And this morning there were like no videos about what happened. And then in the early afternoon, I saw some kind of very. Like you could tell they were rushed. Like one of them, the guy was outside just talking on the cell phone, like just walking, or they were doing like very low res Zoom calls because they didn't have anything scheduled. So it was having their nice, like setup in their house with their studio. They were zooming in because they wanted to get their thoughts out with the shitty internet connections and whatnot. And so I'm like, okay, what do they got to say? And it was like, oh, it was a war crime. And then I just turned it off. Fucking you goddamn pussies. Do you not understand? War crimes only apply to the losers. They don't exist. We made them up. Like we commit war crimes all the goddamn time and we're completely unaccountable because might makes right. That's not like a prescriptive, like, oh, that's the way it should be. That's the way it is. That's the way it's always been. So the United States fucking firebombed Dresden. Abraham Lincoln could do all kinds of shit, including killing protesters, recalling the army to go kill protesters for the Civil War. And he's remembered as this great hero that saved the Union. Everything America did during World War II has been completely whitewashed. And of course, everyone, when you talk about World War II, all you talk about is all the bad things Hitler did. Why? What did Hitler do? He lost. He's a loser. That's all that matters. It doesn't matter what you do. Like this shit about war crimes and atrocities and killing civilians and terrorism. These are mouth noises. They don't matter. All that matters is, did you win or did you lose? If you lose, then you're a monster and all the things you did justifies all the horrible things that were done to you and the world is better off without you. If you won, then all the atrocities and terrorism and the bullshit you did is all washed away and you're a hero, and anything you may or may not have done that was a little bit questionable, it was justified because the people who did it too absolutely deserved it and they had to be stopped, and all this other bullshit. And like all you gotta do, look at the Cold War. Like if you think, if you doubt that the CIA controls ISIS, all you gotta do is look at what the CIA was doing during the Cold War in supporting terrorism. We absolutely sponsored terrorism against Russia in the Cold War. Not only is it not a secret, it's been declassified and it's open. Like they admit it. Now they don't admit what they're doing now. Like now that they're doing it against Russia, not the Soviet Union. Now it's classified again. But it's like you don't need to be a rocket scientist to know that if we did it for all these decades in a row, we'd still be doing it because we are. But but they admitted it what they did in the Cold War. The point is, all that matters is whether you win or not. That's all that matters. So look, I'm not black pilled about what happened to Hezbollah. This is a good thing because the leaders of not just Hezbollah but Iran and probably even Russia. I don't know what it is. I don't know if it's their boomers. I don't know if it's this that they don't know their enemy. Maybe I'm thinking it's like a boomer thing. Because boomers, they get set in their ways. I think it's your neuroplasticity decreases as you age, and there's a certain age where you just don't adapt anymore. Time marches on, the world changes, and mentally, it's still 1994. You haven't adapted since 1994 because that's when your age caused your neuroplasticity to shut down, and your brain just hasn't adapted. And that's fine. Like if you're a doting old man and you still act like it's the 90s, who gives a shit? But when you're leading a country or when you're conducting a war and you haven't updated your firmware in decades, you don't know the enemy you're fighting because you still think you're fighting the enemy from several decades ago. That's a problem. So I think some of these leaders are still stuck in this Cold War mentality, where they think that they thought they could outlast the United States the way that the United States outlasted the Soviet Union. That they could defeat the United States economically by basically causing an arms race, causing them to bleed their economy dry, and then watching them collapse financially from within, and that's how they would win. The same way the United States defeated the Soviet Union. Basically just outlasted them economically. That was the plan. And the difference is, the people who were conducting the wars back in the olden times during the Cold War, they weren't the same kind of people that are conducting the wars now. And one of the reasons, there's a lot of reasons why, but you got to understand that part of it, there's literally a death cult in the kind of Zionist movement, particularly among the evangelical Christians. I'm not exaggerating. It's a literal death cult. The reason why the evangelicals support Israel, it's not because they love Jews, although they do. According to them, when Jesus comes back, all the Jews who want to immediately convert to Christianity will be killed and sent to hell. They have no actual love for Jews, but according to their beliefs, Israel is going to bring about the second coming of Jesus through a massive war. They want to see the Dome on the Rock, which is the Islamic mosque, which is built on the old site of the Jewish temple. They want to see it destroyed. They want to see a great battle of Armageddon between the Jews and the Arabs, and that's going to bring about the second coming of Jesus, and that's going to be the end of the world. And that's what the evangelical Christians want to happen. And what's really funny is the Jews and the Muslims also have the same, more or less, prophecy. So the second coming of Jesus, it's really fucked up. But so the evangelical Christians talk about the second coming of Jesus, but they don't. Before the second coming of Jesus comes what? Who comes before the second coming? The Antichrist, right? You know who the Antichrist is? The Mahdi, which is the Islamic Messiah, who's also more or less a knockoff of the Jewish Messiah. So the Jews are waiting for their Messiah, the Muslims are waiting for their Mahdi, and the Christians are waiting for the Antichrist, so that eventually Jesus can come back. And so there's like.
Oh, TFM is losing its mind. What an idiot. What a complete loser. All right. I'm done. I'm gonna go. See you tomorrow. Bye.